So again, welcome. So today we'll talk about, I will give a quick introduction to Safe AI and our recent progress in Safe AI for self-driving research. So now Safe AI has been identified as one of the critical and emerging technology because of its great potential to protect the security of American people and all the other people, and also expand economic prosperity and new opportunity and realize and defend democratic values. So those items are listed on the critical and emerging technology list update provided by the National Science Technology Council of the United States. Also in Europe, trustworthy and safe AI has been identified as one of the key technologies, and they have reported the trustworthy autonomous vehicle report 2 years ago. So not only the government, but also companies, for example, Google, IBM, Microsoft, and OpenAI have all launched their programs about AI safety. And also National Science Foundation of the US, the universities like Stanford and UPenn, and some NGOs have launched the Safe AI programs. So our lab at the CMU also focus on the safe intelligent autonomy for consequential applications by bridging fundamental learning theories and the practical technologies. So to this end, we have been collaborating with many industry partners, including Ford, Uber, Amazon, Google, Qualcomm, Rolls-Royce, Bosch, Toyota, and Denso, and also work with US National Science Foundation, Department of Transportation, Department of Defense, Department of Energy, and other collaborators. So in general, we started to work on evaluation, and then we started work on robustness, safety, generalizability, embodiment, and also human centricity and explainability. And at CMU, we launched a course called Trustworthy AI, has been one of the most popular courses at CMU with about 200 people enrollment next year. So all those materials you can find those materials online. And particularly, I think safety and generalizability are two very critical components that we can use to deploy our algorithms from not only in simulation and games, but to the real world application, for example, self-driving cars, robotics, and healthcare. So I'll give some examples of our work. So one work is that, so when Uber is the world's first fatal self-driving collision, so our team was invited to work with them to develop a better evaluation and safety improvement algorithms with Uber. So I think that's one impact. Another one is that we work with Amazon. Amazon launched this so-called Amazon Astro that can be used to patrol your home and also have that's considered to be like one of the first commercialized household robot. So how we can design a safe and also generalizable robot. So we work with them for household robot. So in the self-driving domain, we have published one of the first testing protocol with accelerated evaluation when I work at University of Michigan, City. So we are using a self-driving car to test other self-driving cars so that we can generate some safety critical scenarios without really dangerous situation for humans. And also we can dramatically reduce the time for testing. And finally, so for in academia, so we work we collect some data. We collect data from Pittsburgh and develop our own scenario recognition, visualization, and labeling tools. And also we combine all those tools and generative models into our open sourced public platform called SafeBench, collaborating with Professor Bole from UIUC. So we propose one of the world's first accelerated evaluation framework. First, scenario-based data set we call TrafficNet. First open source AV safety benchmark platform, the SafeBench. I think that's still one of the most comprehensive platform. And also today we are hosting competitions and workshop in some international conferences to foster the community. So for today's session, so particularly we want listen to our speakers, new ideas, but also we will see how our participants attend this challenge that we made. They has both vision challenge and also decision-making challenge, both in color. And also we have like a few thousands of safety critical scenarios that run in parallel in color simulation. I think this is one of the first time that we can run such large scale simulation in a very realistic simulator, so that we can use that for example, reinforcement learning applications. And recently our team got awarded from Qualcomm for the safety critical digital twin in the domain of autonomous vehicles. So I think it's not only self-driving car companies are interested, but the chip makers and also key stakeholders are interested in this field. And particularly, so this two of my students, Jiacheng, will be graduating this September and join MIT as a postdoc, and Wenhao will graduate next year. So he is one of the contributor for this survey on safety critical self-driving scenario generation. So in this survey, we summarize 3 key methods: the database approach method, but also scenario generation approach, and also knowledge-based scenario generation approach. So I think with that, each of the methodology has its pros and cons, so that when you do it, you probably want to combine the strengths and weakness of them, and finally you can use a very sparse, insufficient data to generate reasonably well safety critical scenarios. So, well, if you're thinking about hiring Wenhao after his graduation, I think you can feel free to contact him. And finally, the safety critical scenario generation can help us to build a trustworthy reinforcement learning algorithm on a larger scale for decision making. And we have written this survey paper on trustworthy AI with by talking about both safety, generalizability, and robustness. So for example, generalizability, we have introduced many approaches. One of the approaches have scenario generation, but with other approaches like system learning and online adaptation. So and also we know data is at the center, play a central role for any machine learning methodologies. And when we talk about data, we have concern about privacy. So for self-driving car, privacy could also lead to critical concerns. So we also written a survey for safety critical application like self-driving cars with privacy awareness. So you can feel free to also look at this line of research. And finally, so when we talk about safety, we usually need to bring the AI to the physical world. So embodiment of AI is one of the key challenge because the data collection and experiments will be super difficult in the real world. So I think that will be our lab's future focus, how we can really have safety critical AI in the with physical embodiment. So one example could be on the left, you'll see this robotic arm implementation with some vision as an input, and we can study its robustness. And on the right, you can see all those are real-world self-driving cars. You can see their sensors, the configuration of their sensors are quite different from each other. So how the placement and the configuration of the sensors will influence their real-world performance. I think this actually has been well understudied for a long time. And we can see that even with the SOTA algorithms, if you change their layout a little bit, that can lead to about like 5 to 10% of difference. While the difference between those SOTA algorithms are only 1 to 2%. Okay, so with that, I will conclude my introduction. And today we have very excited speakers presentations from Google and also UIUC and Nvidia. So we will start. Our first speaker is Bin Kim from Google Research. So let me see.
Hello.
Hi, hi, Bin.
Hi, I cannot share screen while the other participants.
Give me 1 second.
Gotcha. Thank you.
So we are very happy to have you here.
Very happy to be here too. Let me find the screen. Can you see my screen?
Yes, we can hear. We can see your screen, and everyone can hear the speaker. It's not. Okay, so wait a second. Let me try to status. Oh, here. Okay. Bing, could you test it?
Yeah, testing. Is it working?
Okay. Great. Yeah, it's working.
Wonderful. Thank you.
Okay. Okay, so a quick introduction. So Dr. Bin Kim is a senior staff research scientist at Google Brain. Her research focuses on improving interpretability in machine learning by building interpretability method for already trained models or building inherently interpretable models. She has master and PhD from MIT. Bin is one of the executive board member of Women in Machine Learning and helps with various machine learning conference as a workshop chair and an area chair and steering committee and a program chair. So Bin, so we'll present the thinking about humans to understand machines. So please.
Thank you. Thanks for having me. And sorry I couldn't be there in person. I'll just make a few corrections. I was an executive board member and VP at Wormald a few years ago, no longer there yet, because it has only two-year terms. I'm also from Google DeepMind in this ever so changing landscape of reorg. I'm now part of Google DeepMind. I was in Google Brain before. So putting that aside, I'm going to talk about thinking about humans to understand machines, which is a little bit maybe counterintuitive, but hopefully at the end of this talk, it will make sense to you. This includes work with a lot of amazing folks inside and outside of Google, whose names and pictures will be present as I speak. I'm curious, can we face the camera to the audience so that I can kind of see? I see a door now.
Oh, okay. Yeah, I'll do that. Thank you.
I like looking at.
I'll try to figure it out. You may.
I'll keep going. Gotcha. So things go wrong sometimes. Inevitably, self-driving cars get into accidents. Sometimes maybe it's a system reacted incorrectly in a situation. And some other times it's someone else on the road being a little stupid. And it's not just autonomous cars. Other AI systems also experience failure mode. AI-powered engine being had some inappropriate exchanges with the users, and they ended up limiting the number of exchanges that users can do with this system. And by the way, if you haven't seen this autonomous vehicle collision reports that California mandates all the companies to report, it's pretty entertaining. So you should take a look. Apparently, it turns out that most of the time, it's other cars hitting parked autonomous cars. I find that pretty interesting. And anyway, our hope is that we want to understand how these accidents exactly happened. Was it the car's fault? Was it the human? If it was the car's fault, how exactly, what went wrong? And this talk is about, to understand machines better, we need to actively think about humans, especially what humans cannot yet understand. So what do I mean? To answer that question, we need to think about humans and machines representational spaces. On the left, a circle is a human's representational space, things that we know, dogs and cats, plants, cars. And on the right, it's machines representational space. There's some overlap between the two, M cap H, but there's the space of M minus H, where only machines know. So for example, move 37 that AlphaGo made in its match with Isidore is a great example of this. Now, Go players still talk about this move because we can kind of reverse engineer to rationalize why that was a good move in that particular situation. But we're unable to extract some high-level strategy that a Go player can apply in a different situation. And that sort of thing belongs to M minus H set. And I argue that patterns of unexpected failure of AI systems that we don't fully understand also belongs to this M minus H set. And it's important that I said patterns. It's not just one particular one-off case. It's some extracted concept, abstract concept that some in high dimensional that makes sense, but not yet makes sense to us. So perhaps in some high dimensional space, move 37 might be some generalizable goal strategy we just don't understand. And maybe seemingly one-off failure cases of AI systems like self-driving, in the case of self-driving cars, may have a pattern in some high dimensional space, but we just don't comprehend that yet. So I argue that we need to expand what we know, and that would help us build machines that better communicate with us. If you're curious about work around expanding these two circles, I recommend having a look at my keynote last year. I'm not going to talk about these work in this talk at all, but there are some ways that we can try to expand these two circles. So I'm going to focus today on this set M minus H. In particular, we're going to first focus on this M cap H thing that we've been, as a community, we've been focused on. Main thrust, trying to understand machines, has been in the field of interpretability. But many interpretability methods try to shoehorn this like M thing as a whole circle into M cap H. That's kind of what we've been all doing, including my own work. In other words, while methods know that there exists this M minus H set, something that we can't yet comprehend, we haven't really been doing something actively about it. And I argue that the results that I'm about to show you is an evidence that not considering M cap H and minus H separately has caused a lot of problems in these methods. So let me first define what I mean by explanation. So explanation here, we want to open a box of models and prediction, how it rationalized its decision using explanation. So in the simplest case of many methods look at is given an ImageNet like this. We want to know a pixel, a input feature like xj, how the function look like, the classifier looks like at that xj. So if I increase the xj, does the function go up? Does the function go down, or is it flat? As simple as that. I'm just trying to understand the shape of the function. Now, a few years ago, many years ago, that we stumbled upon this phenomenon that explanations from trained network and untrained network is quantitatively and qualitatively indistinguishable. And we were really just shocked by this. First time we discovered this, we thought it was a bug. And it took us many, many weeks to figure out, wait a second, this is not a bug. So after that work, we had this question of, is there something really weird about this relationship between prediction and explanation, something fundamentally weird about this? So in more recent work, we attempt to quantify this relationship between prediction and explanation. And we leverage causal inference setting. It's really nice because in the world of models, the causal graph is very clear because we made the models and we know what we used to make those models. We used hyperparameters, like what optimizers you used to optimize this network. We decide the architecture, how many layers, what activation function, and so on. And we know which data point went in when I asked, hey, model, what is the prediction for this picture? What's in this picture? And you can draw a causal graph exactly this, and there's like really not many other confoundings that we're missing, unlike a real world case. The question though is that how is each magnitude of these arrows? Like, is hyperparameter influence prediction a lot and prediction influences a lot of explanation, or for some weird reason, hyperparameters directly influence explanation? We don't know, and we can leverage this causal inference framework to quantify those relationships and the magnitudes of these arrows. So that's what we did. You don't have to understand everything in this graph. We'll look at this last graph. In last graph, we're comparing ITE, individual treatment effect of explanation and prediction. The bigger number is, the worse it is. And you can see x-axis is the accuracy of models that you're using. It gets worse as you have more accurate model. And this is shocking. This is not something that we expected, but it's something that happened. So in other words, if you have a model that's just performing poorly, you're okay, because it's your okay region. Prediction is influencing explanation a lot. But if you have a model that's actually good, the one that you might actually deploy, then prediction isn't influencing explanation very much at all. So it's actually get worse as you have models that you're more likely to deploy. And why is that the case? We don't know. We just know that quantifying this showed us that clearly that there's this clear pattern of performance degradation as we have more accurate models. So you might say, well, but sometimes these do work. I used it. Like sometimes it gave me, it gave good insights, and you don't have mathematical proof that these don't really work, do we? So more recently, we do. So more recently, we have this theory work. I work with Blair, who is a theory student from University of Toronto, to really kind of personally kind of closure of all these empirical questions that I had. So again, the question is, given this feature, what is the function of the shape of the function? Now, natural way that we understand these methods is that if the tool gives you zero attribution, then the pixel, the feature, is not used by f of x, and f of x is insensitive to perturbations of this feature near x. And this is how it was explained and advertised in the original method paper, and it's how it's been used. This is a quote from a paper published in Nature, where they use sharp value to determine eligibility criteria for medical trial. So it's pretty serious business that these tools are used in such a way. Our results shows that what seems this very naive or benign inferences that we're making, the tool gives a zero attribution, this feature is unused by f of x, and f of x is insensitive. None of these are actually true, and we can theoretically prove it. The way we do this is we formulate this question of interpreting attribution as a hypothesis testing. So what do I mean? User comes in with an idea that, oh, sharp value tells me that it's a positive, so I'm going to assume I think that function is going up. That's your hypothesis, and null hypothesis would be everything else. And now we test whether sharp or IG or feature attribution methods that has certain criteria can invalidate or validate, help you answer this hypothesis testing question. And that's the framework we start to prove this work. And we show that any methods that has complete and additive properties, and these are very clear, just very intuitive criteria. So complete is every sum of every feature attribution has to sum up to something meaningful, often one. Additive is each property contributes separately. So input feature 1, input feature 2 has separate contributions. Very reasonable assumptions, but it turns out those criteria actually keeps these methods to perform under the line of random guessing. It cannot do better than random guessing. So this is true with the real data. It turns out for 2 concrete downstream tasks that we tested, recourse and spurious features, things that we really care, that both of them hovers around the random performance line. This is the middle line, x equals y line. This is image data that we tested, and many other image data too. However, some cases, they seem to perform pretty well. And those are cases if your model is linear, or the xj that you're testing happens to be linear, then of course gradient or line, which is basically kind of like a gradient-like method, of course they're going to give you a pretty good answer. So here, Avalon, recourse, the green dots and yellow dots, lime and grad doing pretty well. In other cases, however, like look at this wine spurious, everyone is again performing random line. The problem is that you don't actually know which case you belong to. You have a data, you have a method. Half of the time, it might give you the right answer. Half of the time, it will not give you the right answer. And that's the problem, because you don't know which regime you're in. So you might say, oh no, what do we go from here? Well, what do we do then? Well, our suggestion in this paper is that you should just brute force it. You should just do simplest thing possible. If your goal is to find out the shape of the function, function going up or down, flat, we should just sample points around it and see whether function is going up or down. Now, the question then is, how many samples do we need? So in the later part of this work, we talk about how the function that would bring this random line upwards towards better performance. And that is a function of number of samples and resolution that you want and number of features. And this is not some vacuous term. It is actually quite feasible for a lot of cases. So far we talked about what can go wrong when you try to fit in this M into MCAP H. We learned that quite a bit can go wrong. So now I'm going to switch gears and talk about M-H set. How do we leverage this, the machine unique knowledge? I'm going to propose a few first steps. I think there are many, many other ways to do this, but let's first admit our faults, admit our limitations. We don't really know. We don't really know what we don't know. We sometimes don't even know that we don't know. So what that means in Bayesian sense is that uncertainty is really important. We're going to estimate uncertainty. And second, we're going to help humans learn and have humans in the loop so that they realize they learn something new by perhaps extending this blue circle on the left. And we're going to talk about a method where we can change the models and when we can. So let's jump right in. We don't really know what we don't know. We really don't know anything. So this work goal is to design a probe that given a pre-trained model, and their representations, you're going to detect a concept that it knows and it doesn't know. And we're going to do this, not just yes or no, we're going to measure how uncertain the probe is. So probe itself is a measurement device, but it also knows, like, I can give you an answer, but here's extra information on things that in what way that I am uncertain. So what do I mean in what way? There are different types of uncertainty. And here's a really good example of that. Here is a human experiment that McCloskey and Glocksberg did in 1978. Now, how many people in the room think olives are fruit? Who thinks olives are fruit? Who thinks olives are vegetables? Okay. Anyone thinks olives are nuts? Not sure. Wait, so we're confused. So apparently, if you ask this to humans, 60% of people typically think olive is a fruit. And when they say olive is a fruit, although this audience is less certain, maybe it's too early in the morning, they're kind of sure why olives has to be fruit, right? That you have some notion, oh, it has seeds and it has flesh outside. Now I'm going to throw you a different problem. Now I'm going to define a new concept called blicket. Now, blicket is something that I just made up. Now I can tell you that olives in a martini glass, they're blicket. It is blicket. And now I'm going to show you a new picture. that olives on a branch. Do you think it's obligate? Who thinks it's obligate? Who does not think it's obligate? Does not think. Okay, so at least we have less hands raised. It's a little less certain. Why is that? Well, because you simply haven't seen that many blinkets. I just made that up. So you haven't. You need to see more blinkets to determine whether this is a blanket or not. And the point of this paper is that the both predicts outputs 0.5 probability of what the next picture is, and whether it's a fruit or blanket. But these are very two different types of uncertainty. On the left, when we have a fuzzy label, that's called aleatory uncertainty. We just have some fundamental stochasticity in the world. Now, there's a true label, olive is a fruit, but people are just it's just not a clear cut. On the right, you simply don't have data. Once you see more data, then you might be able to determine whether this is a blanket or not. And that's called epistemic uncertainty. It's a very different type of uncertainty and different ways to resolve it. Sometimes epistemic uncertainty, you can just give more data and you can resolve it. But in aleatory, there's just things that you just can't do anything about. So this is what we do in Gaussian process probing. What it needs is a pre-trained model and access to its activations. And given that, we output aleatory uncertainty, epistemic uncertainty, episteme. This is the inverse of epistemic uncertainty, and aleatory uncertainty along with judged probability. Now, this framework is actually really simple. We just leverage the beauty of Gaussian process. So given a model, we're going to have a probe that's a Gaussian process, given observations of data, so duplicate of Martini glass and the new branch, olive branch, what we get out is a distribution of classifiers from which we can sample from. And as you can see, this definition of, for example, aleatory uncertainty is given a particular sample classifier. What's the entropy of each label Y? So this is like something that we can do because we have a distribution of classifiers instead of like one specific classifier. So that's the main difference between the typical probing work and this type of work. And for fun, we tested whether a COCA model, it's a pretty much a state-of-the-art model, and how that aligns with human data. And for fun, like, it turns out that they align pretty well. 60% of the time, COCA thinks the olive is a fruit. And it's not that it's a goal of the paper, but it was just fun to look at. We use synthetic data to validate this method, but another way to validate this method is whether we have right epistemic uncertainty is use it to OD detection. So high episteme means it's in domain. I'm less uncertain. I've seen this data before. Low episteme means out of domain. And we test how well we can do just simply by having that uncertainty measure. And we show that we can do pretty well. This isn't the goal of the method, but just one way to validate that uncertainty measure that we're outputting makes sense. And finally, I find this kind of really, really fun. So we started this work thinking about this paper of Fox and Ullman, distinguishing two dimensions of uncertainty. It's a really fun paper to read. And they define this triangle of rationality, where they say if you are just uncertain, you have low episteme, then you really can't talk about aleatory uncertainty because you just simply don't have enough information. And as you get more and more certain with episteme, only then you can talk about aleatory uncertainty. And we show that GPP follows closely this triangle of rationality that they defined for humans. And some other methods that are perfectly reasonable, technically speaking, does not follow the triangle of rationality. And this is nice because perhaps this can give us humans more information, but still it follows some agreeable notion of uncertainty that aligns with the humans. So next, I'm going to talk about how we can help humans learn, and when we can change the models and when we can change the models. So this work is about understanding emergent behaviors in multi-agent systems. These are some fascinating multi-agent systems. My favorite is OpenAI's hide and seek, where somebody in OpenAI painstakingly went through hours and hours of videos to tag okay, here's their running and chasing. Okay, here there's fort building. Here is a ramp use and so on. And it's so interesting to look at, except I don't know how many hours that person spent to label these interesting behaviors. And the goal is to help humans detect this interesting multi-agent behaviors via visualization. And we want to do this with just assumption that we can observe them. We cannot do anything intervention or nothing. We just can observe their state action pairs, what they do and where they are, etc. And we want to discover behavior clusters given this data. And the way we do this is pretty simple. This graphical model, for those who are familiar with this, we start with an embedding vector, z omega, that describes overall behavior of the system, like are they working cooperatively, are they competing? And that variable generates local behavior latent. So this is an embedding for each agent, how they're reacting and their skill set, for example. And that emits a policy. And what we observe, S and A, states and action pairs, are generated from that policy. And that's the graphical model. And we simply use variational lower bound to infer these latent variables. And here's a simple example how that might be helpful. So here's a running agent, and we assume that agent 0 controls the back leg, agent 1 controls the front leg. And here's something we can offer. This is a joint embedding z omega. This is a z alpha for each agent. User can select an area in one of the agents and see where that maps to in other agent space, and also in the joint embedding space z omega. And see that they compactly map to both of the agent space, and looks like the agent learned how to run. Whereas in this case, this area in the embedding space, it looks like agent is doing something weird. I don't know what's going on with the front leg for agent. And in some other areas of this embedding space, it again learned to walk pretty well. And you can investigate as a human different alleys and different areas of this embedding space. And of course, you can automatically cluster these embedding space to do this, which we didn't do in this paper. And of course, we had to apply this to OpenAI's hide and seek domain because we just really like it. Here, the colors are the labels. We didn't have it. The algorithm did not have the colors, but we just post hoc plotted it because it's just to show that it's nicely aligns with our discovered embedding space. For each agent, Z alpha, you can see that the blue circles, blue dots, which is running and chasing, very fundamental skill set for any agent, has pretty distinct cluster in each of the agent, hiders and seekers, no matter what. Makes sense because it's pretty distinctive skills and a fundamental skill that everyone needs to know. Whereas the fort building, where it's more important for hiders because they build the fort to hide from the seekers. The orange dot is a little more distinctive in the hiders case than seekers. Seekers case, it's kind of overlapping with the black ramp defense. And you can imagine, oh, perhaps if the seekers had known more about fort building, like had more distinct cluster of fort building, maybe they could have find the hiders better. So we can learn interesting emergent behaviors of multi-agent systems simply by observing them. But note that this method does not give you names of each clusters. Humans would have to learn them. And the cluster represents, if the cluster represents just something really, really out there out there behaviors, then it's not going to give you anything more than examples. And also, furthermore, if you have access to rewards and internal representation, that's something you should absolutely use. And this method does not. And now I'm going to talk about a method that where they do use architecture and reward signals. So let's talk about that, to helping humans learn when we can change the models. So in this work, we want to still understand multi-agent behaviors, but this time through intervention. And we're going to build a multi-agent system such that they enable controlled testing and perform as well as baseline. There's a lot of different ways you can do this, but here we're going to leverage something called the concept bottleneck models. The idea is pretty simple. We're going to build in concepts inside of this neural network. So first neuron means the trees, the second neuron means stripes, and so on. Why? Because then at inference time, we can control the model's behavior. So I decided that, okay, zebra, when I'm predicting zebra, don't worry about trees. I don't want trees to influence the predicting when I predict zebra, and I can cancel that neuron out. And we do the same thing in this work where we build in those concepts inside of the one each agent's network. So this network takes RGB input, position, and orientation, and we build this network for each agent. And what happens is this network outputs action, and that action goes back to the environment, take an action, and observation, and so on. And optimizing this is pretty simple. You just have a typical PPO loss plus minimizing the concept to a true label. That's it. Why are we doing this? Well, we can intervene. We can actually have a controlled study, like a kind of medical trial, randomized controls trial almost, and see what happens. And by doing that, I'm about to show you that we can gain a lot of interesting insights. So here's one domain, one of the many domains that we tested is a cooking scenario where there's two agents. There's a tomato, there's a pot, there's a soup, and you got to put the tomato in the pot, wait a little bit, and then when soup is ready, you serve it. And we can also control many different environments of our choice. So we made this impassable environment where they have to coordinate because otherwise you can't serve any soup. Only one agent gets to serve, has access to the serving station. And here in the graph, I'm showing you reward when there was no intervention for agent one and when there was an intervention. And you can see the more they coordinate on the right-hand side, the more degradation of performance that an agent experiences. So that's intuitive, that's obvious, like this is almost like a sanity check. But here's what was interesting to me. So I'm going to draw the same graph, but except this time I'm going to intervene. I'm going to draw it per different concept. So here's a concept of teammate position when I intervene that, how much reward changes, and so on. And here for both of the agents, it turns out the teammate's orientation was the single concept, the single most important concept in their coordination. And I give you a couple of seconds to think about why it's an orientation and not like position, for example. I find this super interesting. And some people it's like intuitive, but it took me a while to realize why. The reason is if an agent wants to go to the tomato, it has to face the tomato first, and then they go. So the orientation is in fact the earliest signal that the other agent can get about next action that the other agent is going to take. And that's why the orientation was the single most important thing and not the position. I find that just fascinating. And you don't have to stop there. You can actually build a graph based on this intervened rewards. And what that means is if you have, if you have a matrix of data points in each row and features in each column, there's a very simple way to build a graph to determine what are the relationships between each data points. And Netflix, for example, does this with the movies, how each movie relates to the other so that we can recommend a better movie. I'm actually not sure if that's the way still they do it, but it used to be the case. And you can build this graph and look at whether the surface behavior, whether two agents just simply have a similar reward aggregation pattern to their actual coordination. So some other domains where there's a social dilemma here, we're looking at a cleanup domain where agents have ones to eat apples. That's how they get rewards, but they only get, somebody has to clean the river so that apples keep growing. And in that case, we discover something really surprising that we didn't initially anticipate. Like two agents just get stuck in the environment physically, and they look like they're coordinating, but in fact, looking at graph, they were not coordinating at all. It was some other agent that caused that incident. So because I'm a little slightly out of time, cover this. Yes, so today I talked about problems of when we only consider MCAP-H, and we can quite a little bit of things can go wrong. And I argue that we really start thinking explicitly about what we don't know and admit it. And by helping humans to learn, we can get better at answering those questions about how these machines fail and what can we do about it. Thank you.
Okay, great. Thanks, Bing. So we have one, maybe we can ask one quick question from the audience here in the room. And if you have questions, you can just walk up and talk with the microphone. If not, there is a question online. So it says autonomous vehicle is usually complicated, including perception, prediction, planning, and control. How do you think we can obtain the interpretability of such a complex system?
Yeah, good question. I think about this a lot because a lot of systems at Google, like you can imagine YouTube is as complex, if not more complex than like a components of system as opposed to one network. I think things like the observational studies that I talked about, that we just pretend that it's a one system and we observe that and infer something to gain some insights, or actually that alone might give you a good idea of, so treat it as a black box, analyze input and outputs and see what happens. But in all that, the point of this talk is that you have to think about what we don't know, that there might be some things that we simply cannot comprehend yet. And we have to know, at least carve out that space in order to really understand what's going on under the hood.
Great. I also have a very quick question. So when you have some safety critical applications, your data set tend to be quite imbalanced. So in this case, when you use some cluster, like non-parametric unsupervised learning to do the clustering, do you think you may miss out some important cases that they are important scenario, but you did not recognize it, so you can now explain it?
Yeah, that's a good point. Maybe we can learn something from non-parametric modeling many work that's been done during my PhD. This was like the hottest thing when I was doing my PhD, that you can control parameters of that, say LDA or Chinese restaurant processes, so that you can give a little more leverage to smaller clusters. So you can do that, and perhaps you can do stratified sampling too, if that's an option. You can simulate more of those mistakes. But I know that in real cases, those unbalanced data sets are really the challenging ones to work with.
Okay, thanks. Let's thank our speaker. Oh, there was one quick.
Thank you for the wonderful presentation. A quick question. I think in one of the slides you displayed like 100 dimension vectors that were visualized, I think, using the stochastic neighbor embedding. I don't remember the exact method, but I'm just wondering, why were all 100 dimensions involved? Why not just the most important ones?
Oh, interesting. Because again, this is a really good question. Because again, like that M-H, we don't know which ones are important. We don't want to leave out the ones that we thought, that's not important, but maybe it is important. Some weirdest thing happens in this OpenAI hide and seek case. So we didn't want to omit anything by imposing our H, because that's maybe the limitation that between us understanding M-H versus M-H.
That makes sense. And then looking now at these decomposed charts, so how can we really visualize them, or how can we interpret them?
How can we interpret these embedding spaces?
Yeah.
Is that the question? Yeah. So
visualize the chart here. How can we?
Yeah, so this work is kind of an interesting work in that we're actually not giving humans recipes, because if we give humans, here's a cluster 1, cluster 2, they're going to think in H space. We have limitation on only thinking in, this is how it ought to work, because we're constrained by the way we're thinking. So this work particularly try to go over that and say, okay, here's a messy clusters, you explore, and trying to connect the dots by yourself, and it's really trying to expand that human's blue circle. So the entropy that I'm introducing here by not giving all the things that we did, all the things that we could have done, is actually pretty intentional.
Great. Sorry. Yeah. Thanks for the sake of time. So let's thank our speaker again, and we'll move to the next one. Thanks, Ben. Yep. Bye.
Thanks for having me.
So now our next speaker is Dr. SSAD. Dr. is an assistant professor at CS at Stanford. So her research interest lies in the intersection of robotics, learning, and control theory. Specifically, she is interested in developing algorithms for safe and adaptive human robot and human AI interaction. She is awarded Sloan Fellowship and SF Career, ONR Young Investigator, Air Force Young Investigator Award, and many other awards, including MIT Technical Trend 35. So without further delay, Dosa, start.
Yeah, of course. Thanks. Thanks for the kind introduction, and thanks for having me today. Sorry that I can't be there in person, but let me get started. So today I wanted to talk a little bit about some work that we have been doing in the space of modeling human behaviors, and what does that mean in the context of autonomous driving, but also just generally, what does that mean in the context of robotics? When I was thinking about this workshop, I was actually having like a difficult time thinking about what to talk about, because I used to work in the space of autonomous driving, specifically safety of autonomous driving and how we think about human behavior models. And more recently, I would say like the past 4 years or so, we have been doing more work in the space of robotics and manipulation, and not as much in driving. So I wasn't sure if I should cover some old work or new work. So I'm doing a little bit of a transition. Some parts might be a little bit of a sharp transition, but hopefully not. I think the trend that brings everything together is this idea of modeling human behaviors, and reflecting on the past, how we used to do it, and how we can envision to do it in the future, especially in the era of large models and large language models and large multimodal models. All right, so let me just get into this. So I started working on autonomous driving around 2012, this was during my PhD. And what we were interested in at the time was actually the topic of this workshop, which is, can we provide guarantees for autonomous cars? Can we provide any type of safety formal specification guarantees when we think about an autonomous car that needs to drive on the road close to other drivers around it in uncertain situations? And the way we started formulating the problem was taking a formal methods perspective. So from the lens of formal methods, the way to go about this problem is to write down a specification, a formal specification that tries to capture the objective of this car and also the environment, and having a very proper environment model, a formal environment model. And then once you have that specification, the goal is to synthesize a controller that is guaranteed to satisfy the specification. And this is known as the problem of reactive synthesis. In formal methods, there's quite a bit of theory around it. It's a very interesting problem because you can provide probably correct guarantees. And we started formulating the problem of autonomous driving under that lens, thinking about the specification. And we had a body of work around this time. So I would say around 2012 to 2016, a lot of my work was kind of in this domain of trying to provide guarantees. And a very common approach towards this problem is to write down that specification formally using some sort of temporal logic specification, maybe linear temporal logic, signal temporal logic. We introduced probabilistic signal temporal logic, adding probabilities. But then the idea is that once you have the specification, you need to translate that specification into a format, into a computational format that you could actually operate in. So in reactive synthesis, you take the specification, you generate a non-deterministic Buki automaton, and then you determinize that. And once you determinize that, you have a thing that kind of looks like a graph, a game graph. And once you have that game graph that captures the specification, you could kind of treat that game graph as a two-player game, right? You could treat it as a two-player game between the system. The system is your policy, your autonomous car, what it is going to do, maybe steering angle and acceleration of your autonomous car. These are the things that you can control. And the environment. And the environment is all the possible other things that could go wrong in the environment. The light turning red or a car cutting in front of you. So that would be the actions of the environment. So we end up with this game tree, which is basically a game between the system and the environment. And if we can solve that game, we can find a strategy. We can find a strategy for the autonomous car, for the system, and that would be a provably correct strategy that will satisfy, guaranteed by construction, the specification. So there's a lot of promise here, but it's also pretty exciting that you could actually do that using reactive synthesis tools. And the interesting thing is, like, the moment you have the game, like, you can think of this as an adversarial game. You can think of like GANs, like almost like as a version of like what this game would look like. Solving the game is actually not that hard. It's polynomial time, but there are a lot of other things that are hard in this picture. So one of the things that are hard is once you have that specification, kind of bringing that to a format that you could operate in, going from that specification to a game, that takes doubly exponential time in the size of the specification. So that is super expensive, right? Like if you actually want to treat this reactive synthesis problem formally and correctly, right? Like you would end up with a doubly exponential time algorithm. So that's one problem. There are a number of other problems here. Oftentimes, you don't know what to write in the specification. We say, well, safety, but what does that actually mean in the context of an autonomous car that does have like different components that come in together? It has a perception system and a control system. Like what is the specification is oftentimes ill-defined. And a lot of work that I've been actually doing since like 2016 is focused on figuring out what that specification is, trying to learn that from data, trying to think about like the value alignment problem. That's all like going after figuring out what the specification is. So that is also like another part of this problem that is hard. And then the third part of like this slide, this particular approach that is hard is that oftentimes this approach of reactive synthesis works really well when we have discrete systems, right? Like this temporal logic specifications works really well with like discrete time and discrete space. And the moment we go to the continuous land, then we need to like worry about the gap between the discrete and continuous abstraction and abstractions. And that ends up blowing up fairly quickly if you want to discretize super finely. And if you want to treat things in the continuous land, then the same like we will not have the same level of guarantees that we would have with reactive synthesis. So there is kind of like that balance, that trade-off between like how large of a system we can talk about versus what type of guarantees we can provide. And that is a little unsatisfying because when we talk about real systems, then we start losing guarantees or we start losing like some of these statements that we might care about. But anyway, so I was working on some of these directions. And one problem that got me really excited around like 2014, 2015 was that oftentimes when we write this specification, going back to the specification question, we need to put down some sort of behavior model or human model of how other cars around us drive. And this human model at the time, like the thing that we would write down was the most generic, obvious thing that I, as a designer, would decide human-driven cars are driving by. So the model at the time, if you look at actually the papers around that time, was that let's try to estimate what is the velocity or acceleration of this other car right next to us. And then let's just project that. Let's just assume that they're going to go with that linear velocity for the next 5 seconds. How bad can that model be? So that model is super simplistic, and we could provide guarantees with that model, but it was very unsatisfying that this model of human behavior that we are putting here is just wrong. And the guarantees, then that makes the guarantees kind of like incorrect. And the thing that I got excited about was, well, really the challenge falls into how we are modeling humans. If I model humans as adversarial agents, then I might just not as well like leave the house, because if they're adversarial, then there are going to be accidents, and what is the point of the guarantees? And then if I model them so simple, like in a simplistic way, right? Like think about, oh, they're going to follow like linear velocity. That does not capture the full behavior of humans, and that will not capture some of the risks and some of the safety measures that could come up. And around the same time, right, like all the car companies were trying to put out their cars out, and we started seeing behaviors that kind of looks like this, which is if you model human-driven cars based on like how we think by the rules of the book they would drive, we would not be able to perform interactive maneuvers. So in this case, like the Waymo car is in an exit lane, and it needs to exit and come back around. And part of the reason is that it is not acting in an interactive way. And part of the reason is that potentially the behavior model that is part of the system is not capturing like the full spectrum of interactions that goes on between cars, the negotiation that happens between cars in a task that is changing lanes, which is as common as changing lanes. We need to actually like think about better models of human behavior. Because if you think about it, if you use that linear velocity model, none of these cars would be slowing down for you. Under the linear velocity model, you actually do have to exit and come back around because your model of humans like is incorrect. And how is it that we as humans change lanes? Well, we realized that we can influence people, right? Like we realized that we could actually, let me just go to the slide. We realized that we could actually nudge in front of people. And when we nudge in front of people, that linear velocity model would be incorrect, right? Like people will actually slow down because we nudged in front of them. So this kind of like introduced a whole body of work that we started doing around 2016, 17, which was really like focused on building better interactive autonomous cars and interactive robots that do take into account the human robot, the human autonomous car interaction that goes into a lot of these coordinative, collaborative settings. So the way we modeled this at the time was in a game theoretic perspective. So we said, well, I have this autonomous car. The autonomous car should try to optimize its reward function or its objective, and that depends on states and actions, which is usual, perfect. But it also needs to depend on a human model, like what the human does. And what the human does is this UHS star here. And the way we modeled what the human does here was based on collecting some amount of data and assuming that humans are also optimizers of reward functions and trying to recover that reward function. So here we decided to do inverse reinforcement learning, right? Like we said, well, humans they are probably optimizing some sort of objective. They don't want to collide. Then they also want to have like some sort of distance with other cars, but like they also want to get to the goal as fast as possible. So maybe we could write down a reward function that captures that. And maybe we can learn the parameters of that reward function by collecting lots of data of how normal drivers drive. And that would be our model of the human. That was a decision that we made at the time. And I actually think that was an okay decision. But there are a number of problems with this formulation too. And one particular problem is that not all humans are the same, right? Like if I collect driver behavior of like generic normal drivers, that is going to give me some model of human behaviors, but that doesn't really capture the full spectrum of human models that we see when we drive like around different drivers. So how can we address that, right? Like that kind of like builds up on top of like this question of human modeling, behavior modeling. We did the simplest thing, but that simplest thing is not going to capture everything. And with that simplest thing, sure, we could try to like cut in front of people and they would slow down for us. But like maybe that is not the best strategy. Like if I have a distracted driver right next to me, or maybe an aggressive driver who's not letting me in, I should not try to cut in front of everyone. So what we decided to do was to add a parameter that tries to capture really this driving style and driving behavior. So the idea then was that maybe I would just have a parameter, let's call that theta. And this theta parameter is going to capture, oh, if this person is aggressive or timid or distracted or attentive. And I could have a belief over this theta parameter and just update that belief based on my observations. So this is very similar to having any parameter about the environment and then doing passive estimation, acting in the environment and trying to update our belief over things that we are uncertain about. The thing we are uncertain about here is something about the internal state of this human driver. So it's something about the human, but it's interesting that in a similar way that I would do perception about the environment, I could do perception about this human and the state of the human. So we kind of like built on top of the original model that we had. This original model was that we have a reward function, which is a function of states and actions. And we say, well, actions of humans is proportional to exponential of the reward function. But now we could say the reward function is parameterized by theta, right? Like by this driving style. And we'll just have a belief over that and we update. The more interesting thing is that we could also actively gather information about this theta, about this driving style. Like oftentimes, right, like in perception, we might do passive estimation, but we might be interested in doing active perception, actively gathering information in the environment. And similarly, we could do active perception over the driving style of the person. And it turns out that if we do active perception, we would end up getting behaviors that are extremely human-like, right? Like we would end up like nudging in front of people and then based on that gathering information. And if we decide that this driver, this white car driver is distracted, we would go back to our lane and we would realize that we should not be cutting in front of them because they're distracted. So it's kind of interesting that we get the nudging in behavior, not by hand coding, but by optimizing information gain over belief of driving style and the rest of our objective. Like we automatically get the nudging in behavior because now we are trying to actively gather information about people. All right, so that was my quick summary of some of the earlier work that we did in this domain, right? So the key idea that we had in these earlier works was that if you have an autonomous car or a robot, their actions influence the actions of other drivers, and we should be mindful of those influencing behaviors. Like drivers don't drive in isolation, autonomous cars don't drive in isolation. We need to think about influencing behaviors, and we maybe need to leverage that for better safety, efficiency, coordination, and even estimation, right? Like when we're trying to gather information about them, that is a form of estimation. And these influencing behaviors can really help us get that information. All right, so that was all great. But then we started looking at a particular scenario, like we started thinking about risk and safety a little bit more, which is again, like close to the topic of this workshop. So the models that I described, they capture driving behavior in most normal driving scenarios. But what if you're particularly in a near accident driving scenario, near the end of the risk spectrum? Do these models still capture that? So that was a question that we were interested in, like building on top of these body of works. Like we were like, okay, so does that capture everything when we are thinking about near accident scenarios? So let me show an example of a near accident scenario. What do I mean by that? Let's say that these two cars are approaching the intersection and the light turns yellow. And I have this blue car, and this blue car, its light turns yellow. And we don't know if the blue car is going to actually stop or is going to pass the yellow light or the red light. And the red car here on the other side, the upcoming red car, that red car is deciding to make an unprotected left turn, right? If the red car is deciding to make an unprotected left turn, it needs to have a fairly good estimate of what the blue car is going to do. And if it doesn't appropriately model the blue car's behavior, the human model's behavior, it might decide to take actions that are just not safe and lead to accidents. So the question was, can we better model the behavior of the blue car in kind of like these near the end of the risk spectrum scenarios? And if you think about optimally what humans would do, well, the optimal solution might actually be, oh, you got to stop at the yellow light or red light. But I would argue that that is not necessarily the thing that all humans do, or like that is not necessarily the most common thing, right? Like I pass yellow lights like all the time. Maybe it's not a good idea, but like that is a thing that I end up doing in a lot of these scenarios. So when we are building these autonomous cars or when we are building these robots, they should really recognize that people tend to behave suboptimally in risky scenarios, and we need to capture that suboptimality somehow. And so far, the model that I've shown everyone is this model of optimizing expected return, right? Like this is this very utilitarian model that says, well, how do humans act? The way they act is probably by optimizing some sort of reward function, maximizing sum of rewards, and that is their action. So the optimal action is the thing that this rational human is going to act. And I'm using the term rational here actually like incorrectly, because like you might say, well, humans are rational under bounded memory and bounded time. Like rational does not necessarily mean the same thing as optimal. What I really mean is that the model so far we have used is that humans are going to be optimal given their reward function that is learned from data. And soon people realize that humans are stochastic, so they're not going to deterministically optimize this reward function. So there are a number of models that follow up this utilitarian model that try to capture the stochasticity. And oftentimes, a very common model is this noisily rational model. So the noisily rational model, what it says is that let's just add a little bit of noise. Let's sprinkle a little bit of noise on top of the optimal action model. So let's say that probability of actions of humans is probabilistic and is proportional to exponential of not just the reward function, but a theta parameter, a temperature parameter times that reward function. And this temperature parameter, let's call that the rationality coefficient. And if you think about this theta parameter, if it goes between 0 and 1, it takes you anywhere from the optimal action model to random human, right? So you could go between random human and kind of like the optimal human model based on playing around with your theta parameter. And in practice, theta could be a hyperparameter that will learn, but it does capture this noisily rational model of the human, which is good. I think it's better than the optimal action model. But there's a big problem with this noisily rational model. And the problem is that it actually does not capture how humans act near the end of the risk spectrum. Specifically, like if you look at like that last example that I was giving, it turns out that in that scenario and in a lot of other scenarios, the most likely action that people take would be something different from the optimal action. And the noisily rational model does not capture that. With the noisily rational model, no matter how much you change your theta parameter, the most likely action would still be this optimal action. And that turns out to be incorrect, right? Like in practice, if you look at very much, like risky scenarios, like people end up having a different action that turns out to be the most likely action. So what we have proposed in this HRI work in 2020 was that maybe we should adapt that model. Maybe we should have a slightly different model built on top of the noisily rational model to capture this risk-aware behavior of humans. And the way we are doing that is by tapping into ideas from behavioral economics, specifically cumulative prospect theory, as a way of changing our reward function so that we can better capture human behavior in these risky scenarios. So the model that we have started looking at is that human behavior is going to be probabilistic, and probability of actions of humans is going to be proportional to exponential of theta times r, but this reward function is going to be an adaptation of the original reward function that we had. And that would allow us to try to capture risk. So if we think about the reward function, right, like the reward function is going to be a linear combination of probabilities of events times rewards of taking that particular action. And these probabilities and rewards, like the way that we would address them in the prospect theory perspective is to adapt both of them, to make nonlinear transformations to both the probability and reward to try to capture human behavior in risky scenarios. And let me just like briefly talk about how one would go about that. So if you look at the reward function, if the true reward is the dotted line, it turns out that if you look at human behavior in high reward and low reward values, human behavior would end up having different slopes compared to the true reward. It would have smaller slope when we are in high reward scenarios, and we'll have a larger slope when we are in low reward scenarios. So basically, the transformation on the reward, the nonlinear transformation on the reward, is what I'm writing here as this V function. And it does have like a number of hyperparameters, alpha, beta, and lambda, that tries to capture how humans act in these scenarios. And what this is really capturing is exactly the same phenomenon of trying to compare like the value of, let's say, $1 versus 10K, right? Like if I ask you $1 versus 10K, like how much value are you actually putting on that? Like 10K seems a lot of money. But if you're talking about $1 million and $1 million and 10K, all of a sudden that 10K does not have like that much value, right? Like the moment we're talking about these larger value situations, right? Like 10K will not have as much value as it would in this other case. And then that is the same phenomenon that we start to see when you're looking at high reward scenarios, like having this smaller slope. And this is a particular nonlinear transformation that is super well studied in prospect theory and behavioral economics. And one could argue that we could bring in the same ideas when we are looking at driving. Similarly, we could look at the probabilities, and also similar to the reward, probabilities are also going to be adapted to some extent. So when you're looking at the true probability being the dotted line, the high risk scenario, the risk averse scenario, we would basically correspond to the orange line. And what this says is that if you're looking at low probability events, we as humans, we tend to overweigh low probability events, but we tend to underweigh high probability events. So there is going to be kind of like another transformation parameterized by gamma here that tries to capture our behavior when we think about high probability versus low probability events. And again, this is exactly the same phenomena that we see when we buy lottery tickets or when we buy insurance, right? Like we actually have a hard time like thinking about these low probability events. And because of that, we tend to take actions that are not optimal, like with respect to the true reward function. All right, so how do we go after like learning a model of human behavior when we think about prospect theory and adapting the reward function? So we decided to do a study in the case of autonomous driving as well as in a robotic scenario. I'm not going to be talking about the robotic scenario here, but just very briefly, in the case of driving, in this particular near accident driving scenario, we decided to run a study where we collected some amount of data of how humans drive and what decisions they would make when it comes to this like intersection scenario. And indeed, humans tend to act suboptimally when it comes to these intersection scenarios, like where we are kind of like near the end of the risk spectrum. And what we decided to do was we took this data and we learned these transformations, these hyperparameters that allow us to have this risk-aware model of the human that is based on the prospect theory reward function. And using this model and comparing that, I'm comparing that with the noisily rational model that I was showing earlier. What ends up happening is that we get better alignment when we are looking at high risk and low risk scenarios, better capturing the behavior of humans in this particular driving scenario. And the noisily rational model would not really be able to capture that, which I think is important when we think about, again, like near accident scenarios, we need to really think about risk carefully. So let me try to wrap up here. And if I have like 5 more minutes, I would like to talk a little bit about some of the directions that we're exploring from here. So far, I've talked about human modeling. And we talked about different ways of modeling humans using a reward function, trying to adapt that reward function in an online fashion, doing estimation. And then in this last part, in this HRI work, what I discussed was how we can capture suboptimal human behavior by using these risk-aware human models based on ideas from behavioral economics. All right, so that's all great. But if you think about it, a lot of these prior works that I've talked about either like assume small amount of data, collecting small amount of data and learning the reward function, or thinks about like online estimation, right? Like how do I online in a quick fashion, like adapt my model and realize what type of driver I'm dealing with. But in the day and age of large models, in the day and age of like foundation models, we are potentially going to have access to models that can be pre-trained on large amount of data and representations that could actually be pretty useful for many different downstream tasks. So the idea of foundation models is that let's collect lots of data, let's train this representation, and then fine-tune it for many different downstream tasks. And we see kind of like a similar paradigm in robotics, right? Like in robotics, I could have on autonomous driving, I could have data of robotic interactions, I could have videos of humans, I could potentially have language narrations or instructions. I could have a lot of simulation data. And then taking this data, the question is, can we try to learn a representation, a multimodal representation that's learned from this multimodal data and make sure that that representation is useful for many different downstream tasks. So the thing that I'm excited about today is how we should go about that and what would that mean in the context of modeling humans, in the context of autonomous driving, and how should we think about this problem? So let me just briefly in the next 2 or 3 minutes, talk a little bit about some of the more recent work that we are exploring in this domain and try to connect the past to the future. So if you think about representation learning for robotics, there are often 2 extremes. And both of these extremes try to learn visual representations. We had at CVPR today. So at CVPR, I imagine like there's going to be a lot of discussions around visual representations. And the visual representations that are present today that are not grounded in robotics oftentimes fall into these 2 extremes. One extreme is using things like mask autoencoders. So start with an image and then mask it and try to reconstruct that image. And these representations are really powerful because they capture quite a bit of information about the syntax of the task. They capture local and spatial features. If I want to do grasping, like really detailed things, I would be able to capture that knowledge in these types of representations. And they allow me to do pixel reconstruction. They allow me to learn patterns within an image. And that is really powerful. But they have a big problem. And the problem that they have is that they destroy all semantics. If I have an image of orange juice versus an image of like a jar of orange juice versus a jar of milk, right? Like they will have very different representations because the pixels look different. Like one is orange, the other one is white, right? They're very different pixels. And because of that, I wouldn't realize that, well, pouring orange juice versus pouring milk, like they end up being fairly similar. I lose semantics. I lose the fact that there are some similarities here in terms of the affordances of the task. So then we can talk about the other end of the spectrum. The other end of the spectrum are things like CLIP, for example, where we try to align representations that come from trying to get language supervision and align language and text together. So try to learn concepts across images. These are actually like wonderful because they try to capture quite a bit of semantics, like pouring orange juice versus pouring milk, like they are the same task. So we would end up getting similar type of representations there. Okay? But the problem is that they destroy the local features, right? Like they destroy like the detailed like task information that you would need when you think about like picking up an item. So running out of time. So let me just try to talk about how we are addressing this problem. So the way we are addressing this problem is by capturing syntax and semantics together, by using language as a way of grounding these representations. So we do grounded reconstruction by conditioning our representations on language data. That way we get really the best of both worlds. So the model that we have trained is called Voltron. It's going to be presented at RSS. And what Voltron does is it's this language-driven representation learning. And this is work that is a collaboration between a number of people. Sid Karim-Chedi has been leading this work. But the interesting thing about Voltron is it tries to capture syntax and semantics, and even a little bit of context and dynamics of the task. So we start with a mask autoencoding backbone. But then the additional things that we add to this mask autoencoding backbone is language captioning, language generation. Let me go to this image. So we do language captioning, language generation, and we pass in multiple frames. So we try to capture context as well as quite a bit of information about grounding the representations for various types of tasks. This is trained on large amount of data and is fine-tuned on a number of downstream tasks. And it outperforms a number of other prior representation learning works like R3M, CLIP, MVP, and it actually works on a number of different downstream tasks. The last slide that I want to talk about is here because I do want to connect it to this idea of capturing intent, right? Like if you think about capturing intent, I talk about human models capturing intent. These types of pre-trained representations, they're actually pretty powerful in terms of capturing human intent. If I pass it a new video that it hasn't seen, Voltron, kind of like zero shot, is able to figure out what the human intent is, in this case, opening the faucet. And even if I put a robot video, it is able to do that zero shot, capture human intent. So this is something that will be presented at RSS. It is open source. Please feel free to use it. Pip install Voltron robotics. And happy to talk about this offline too, but I think these types of models can also help us better understand what sort of human representations we have. All right, so let me just stop here.
Okay, great. So for sake of time, we'll directly switch to the next speaker. But also I want to guarantee you that this is the perfect topic we want to listen, and because all the technology should be able to share across different autonomy, including cars and robots and everything else. And again, super excited to see you have covered so much, like a big spectrum of all the problems. And we'll keep in contact. Yeah, we'll keep in touch. Bye.
Sounds good. Thanks for having me.
Okay, great. Okay, so we'll move on. So our next speaker is Marco Pavol. So Marco is a associate professor in the Department of Aerospace at Stanford. He also serves as director of autonomous vehicle research at Nvidia. His main research interests are in the development of methodologies for analysis, design, control, and of autonomous systems, with the emphasis of self-driving cars, the aerospace vehicles, and the future mobility system. So Marco, please.
Thank you very much for the introduction. Can you see my slides okay?
Yes, we can see your slide and I can hear you very well.
Okay, great. Right. Thank you for having me. So today I'm going to highlight some of my work toward building trust in AI for autonomous vehicles. Now, AI, and in particular machine learning models, are clearly ubiquitous in modern autonomy stacks. AI models have been dominating the perception field since roughly 2014. Similarly, AI models are now at the core of most prediction algorithms. And while AI models are not as predominant yet for planning and decision-making tasks, they're certainly gaining traction. And this is for a good reason. AI models and AI-based reasoning, more in general, are uniquely suited to cope with the vast diversity of scenarios that an autonomous cars can encounter during operations. But AI models are not perfect. AI models, for example, may not have enough semantic understanding of a scene to adequately reason about a vehicle on a trailer or a low-flying bird, as shown on the left-hand side of this slide. Or they may not be able to properly handle the unavoidable uncertainty that might arise in some situations. For example, in the top right example, where it isn't clear if the person on the right is a pedestrian or a cyclist. Or more simply, they might get confused by out-of-domain objects. That is, objects that were never seen during model training, which may cause erratic responses. A common approach to design safe AI-based systems is to complement AI components with classical rule-based algorithmic pipelines without the common causes of a failure. For example, fusing the output of a learned perception architecture with the output of a classical perception architecture through a hand-tuned rule-based fusion system. However, this requires additional computation. And more importantly, this can limit the performance gains achieved through the learned fusion pipeline. So the question is, can we complement such an architectural approach to safety by leveraging advancements in algorithm designs in terms of explicitly accounting for safety assurances as part of the design and operation of AI models? The end goal is to fully harness the capabilities offered by AI models while easing as much as possible the need for extra architectural components. This purpose, our research on algorithmic AI safety targets advancements in how we design the AI models, how we deploy them, and how we maintain such models throughout their life cycle. Specifically, work on design time assurances, whereby we develop techniques to robustly train machine learning models, along with techniques to provide calibrated uncertainty estimates for the outputs of those models. Second, complementary to design time safety assurances, we work on deployment time safety assurance methods that monitor the behavior of AI models during operations in order to trigger fail-safes if we detect erratic behavior. And finally, at the product lifecycle level, we work on techniques to rigorously evaluate model performance on a given operational design domain, along with tools to store and level at least part of the data to improve data-driven models, for example, to address failure modes. And I argue that such a multi-pronged approach is necessary in order to achieve the level of trust required for safety-critical autonomy, and in particular, autonomous driving. So in this talk, I'll discuss our ongoing work in two main areas, namely simulation for the evaluation and development of autonomy stacks and anomaly detection. Starting with the topic of simulation. Now, simulation is in many ways the holy grail for the development of autonomy stacks. Here I'm showing an example from the Nvidia DriveSim simulator. However, we're still not ready yet to use these simulators to fully validate the end-to-end performance of a driving stack. And arguably, the key missing piece is that the behavior of the simulated human agents, such as cars and pedestrians, are still typically controlled by rather simple hand-tuned models. But the real-world driving behaviors, of course, are much more complex and nuanced. So the question is, can we build intelligent agents to generate realistic human-like driving behaviors in simulation? Now, in the past few years, there has been a lot of progress in modeling human behaviors for the purposes of trajectory forecasting. That is for the purpose of predicting where the agents on the road would go in the next few seconds. And this is also the topic that Doris, of course, talked about. In particular, in my lab at Stanford, we've been developing a fairly general generative model to forecast human trajectories, whereby the idea is to learn a distribution P about the future human actions, and here denoted by U sub H T plus 1, conditional on the history of an interaction denoted by X in U and highlighted in gray, as well as a candidate robot action sequence denoted by U sub R T plus 1 and highlighted in purple. The interaction history represents, for example, the history of relative poses between the autonomous vehicle and the other agents on the road. And conditioning on history lets infer things about the human driver like aggressiveness or alertness. And conditioning on the autonomous car's future lets us capture the interactive aspect of an interaction. Our framework called Trajectron++ is based on a conditional variational autoencoder model and can ingest as conditioning variables a vast set of heterogeneous data from dynamical information. Clearly, a pedestrian has dynamics different from those of a car, all the way to maps encoding information such as road boundaries and crosswalks, and even human silhouettes, in order to properly predict pedestrian movement. We have thoroughly tested the Trajectory++ in closed loop with the planning algorithms on a test vehicle at the Center for Automotive Research at Stanford. The role of a human-driven vehicle is taken by a small RC car, which is remotely controlled by a student. We use an RC car in this experiment since we want to stress test our algorithms in highly interactive situations, traffic weaving in this case. And clearly, we want to make sure that nobody gets injured in case of a failure. Elements of our research have been incorporated in the prediction network that is currently in use within the Nvidia AV product, referred to as PredictionNet. Here, forecasting agent features in a highway merge maneuver. Of course, the task of predicting what humans will do in the future is quite close to the task of emulating in simulation how a human could behave. So the question becomes, how can we extend such a generative prediction models to build realistic traffic models? Concretely, we have 4 key desiderata for simulation traffic models, namely fidelity. Can we synthesize agent group behaviors that resemble real-world traffic? Diversity, can we generate a wide range of realistic traffic patterns? Controllability, can we steer the traffic model to generate a specific scenario? And adaptivity, can we adapt to new regions with little to no tuning? But we face a number of technical research challenges. In particular, stability. We want to prevent the simulation from diverging out of reasonable behaviors, and long horizon simulation. Ideally, we want to run the simulations for minutes or even hours with a horizon much longer than the training data horizon. As mentioned previously, we have a good idea of how to model human driving behaviors for the purposes of real-time trajectory prediction. But can we just use a prediction model to simulate interactive agents? And the answer is not quite. For example, the left video is a sample driving trajectory from a real-world driving log. As shown on the right video, if we just follow the most likely trajectory generated by a prediction model and we close the loop on it, the agent quickly diverges from a normal driving behavior and stops in the middle of a road. And the fundamental reason behind this divergence lies in the prediction model errors that accumulate over time and eventually cause the machine learning model to diverge from states that it knows how to handle. The model then ends up in an auto-distribution situation and its output becomes erratic. So basically the model freaks out. To address these limitations, we have developed a hierarchical decision-making framework that disentangles the imitation problems of modeling high-level intent and low-level control. Essentially, we are emulating how we as humans make decisions on the road. First, we decide where we want to go, and then we make low-level decisions about how to get there. Shown in the left video, the high-level planner learns to set goals by sampling from a spatial probability map shown on the right. A goal conditional policy makes low-level control decisions to reach the target. The policy uses a vehicle kinematic model to generate the physically plausible motions. So there are a lot of details here, but the key insight is that such a decoupling approach is key to achieve stable simulations over very long horizon, as it significantly simplifies the learning problem and therefore enables better generalization. So with this framework, we can create diverse scenarios by controlling all the agents within a seed. The vision is that in this way, we can generate countless realistic traffic patterns, which can be readily parallelized and used to allow an autonomous vehicle stack to accumulate an unprecedented amount of realistic experience in terms of interactions with the human agents. And we can also envision alternate evolutions of a scene, enabling counterfactual reasoning. A natural question is to what extent the behaviors we generate are plausible and realistic. And designing evaluation metrics for traffic simulation models is indeed very, very challenging. There are no simple quantities that can summarize behavior realism, and we cannot easily compare with ground truth datasets, as our goal is to generate new and diverse simulation rollouts. To address this problem, we consider 3 types of evaluation metrics in order to measure simulation performance. The first are rollout metrics, which directly measure low-level trajectory information, such as how much area is covered by repeated rollouts, how varied rollouts are from one another, and how frequently there are collisions or off-road driving. Second, we have statistical comparisons, which compare simulated distributions of dynamic quantities like a speed or jerk to real-world data distributions. And finally, we have learned human likeness scores, which evaluate the simulated trajectory likelihoods using a probabilistic prediction model trained from real-world driving logs. Viewed altogether, these quantities paint a picture of the strengths and the weaknesses of the different traffic models. And as can be seen, our method, which we call the bits and whose corresponding bar is in green, broadly outperforms prior traffic simulation approaches. So far, I've shown the methods to produce a high fidelity and diverse simulations of human driving. As I mentioned earlier, another important desideratum is to be able to make these simulations highly controllable. That is, to steer the simulation towards scenarios that are particularly useful for simulation and validation, for example, cut-in driving scenarios. But this is difficult, primarily due to the opaque nature of neural network models. So to this purpose, we have recently developed a methodology that leverages a differentiable logic to guide the generated trajectories to meet rules defined using a particular type of logic referred to as a signal temporal logic. In particular, we harness the power of diffusion models and guide their denoising process with the gradients of a user-specified STL signal temporal logic formulas, yielding outputs that adhere to the rules. As an example, say we wish for some vehicles to stop in certain regions. The top video shows the original simulation from bits with no guidance, where the three vehicles on the bottom lane move straight through the intersection and subsequent road. In the bottom video, we added rules which enforce that those specific cars stop within the marked areas. I mean, this is just, of course, a toy example to show you how we can actually guide the simulation toward a desired outcome. This methodology provides a convenient way to guide a data-driven traffic model toward behaviors that realistically emulate scenarios with specific characteristics. For example, some of the drivers could be inattentive and might fail to stop at a stop sign. And now we can generate these rare but extremely important scenarios almost automatically. Where we're going with this is to devise a text-to-simulation of sort, whereby we use a powerful large language model to encode natural language specifications of desired simulation settings, which can, for example, be police statements describing the conditions that led to a collision. This application can then be internally translated into STL rules and enforced by them, thereby yielding simulations of real-world collision scenarios. As an example, our latest work is able to factor in the specific instructions from this prompt to simulate a scenario where two vehicles collide in the desired manner, from left in this case. So view this as a sort of generative AI on steroids. It's not really text to image, it's not text to video, it's really text to simulation, text to behaviors. Here are some more examples of a reconstruction use case where we took crash scenarios recorded in a National Highway Traffic Safety Administration crash database. Note that this database is mainly comprised of text-only descriptions of crashes, which can now be harnessed by our text-to-simulation framework. Our method also enables editing of the generated scenarios. Here we can see the various iterative changes that a user can make to an internally generated scene. To implement each of these efforts, we have developed an extensible traffic behavior simulation framework called the TBC. This framework provides necessary infrastructure, such as a simulation environment, a training pipeline, logging, visualization, and a powerful suite of supporting utility functions. We also include a number of popular traffic models, including BITS, our state-of-the-art deep learning traffic model, specifically designed for closed-loop simulation. This framework also supports initialization from multiple datasets with our unified trajectory data loader, referred to as track data. And along with models, we also provide a suite of metrics to evaluate simulation models, including behavior statistic coverage, and diversity, as I mentioned before. So if you're interested, this framework has been open source, and it is available at the link that is provided in this slide. Summing up, the key takeaway is that generative AI is the key enabling tool for us to achieve a high-fidelity, diverse, and controllable simulation that can then be used for safety evaluation. We're currently investigating a number of directions related to simulation, including combining, as I mentioned, large language models and behavioral models to enhance diversity and controllability, devising techniques to efficiently adapt behavioral models to a handful of data collected online or offline, for example, by using meta-learning ideas. And the results along these directions are available in a paper that we recently presented at ICRA 23. Third, devising high-fidelity pedestrian models and more broadly models of other agent types, for example, cyclists. Fourth, defining ways to best integrate such a sim capability within a safety evaluation workflows. And finally, we are setting up and releasing dataset and sim infrastructure to catalyze research on this topic, for example, the TBC framework that I mentioned before. Now, advanced simulation can significantly help with refining the design of an autonomy stack and therefore reduce the sim to real gap. Unfortunately, on the other hand, at deployment time, there might be still so-called unknown unknowns, unpredictable conditions, and that can still lead to mistakes. Therefore, the next question is, how do we catch and address such anomalies in real time to mitigate system-level consequences? And we've worked extensively on this topic, but in this talk, I want to focus on a specific class of anomalies that we are particularly interested in at this time, which I refer to as semantic anomalies. Concretely, let's take a look at this video from a Tesla display. At first glance, the visualization looks completely nonsensical. But after a few seconds, and especially after we see what the actual scene looks like, we as humans have no trouble understanding what's going on. The reason why there is this infinite stream of traffic lights is because there is indeed a truck that is transporting traffic lights. Or here, there is another example, this time of a stop sign on a billboard causing trouble. So the interesting thing about these cases is that at the object level, you can't really say that, for example, the detector is malfunctioning. The detector is correctly identifying that there are traffic lights or that there is a stop sign, but of course, in a way that does not really reflect reality. So we call this class of problems semantic anomalies. That is, edge cases unseen in the training data and caused by an unusual and a tricky combination of in-distribution objects. The semantic anomalies induce system-level autonomy failures, like, for example, ghost breaks in the two examples that I provided here. And while the semantic anomalies can be very difficult for system designer to foresee at the design phase, the key is that just a little bit of contextual understanding is all that an autonomous vehicle would need in order to detect them and reason about them. So for this, we turn to the emerging capabilities of foundation models, specifically large language models or LLMs. Here we have recreated the first scenarios in the Carla driving simulator, and we can see that the autonomous vehicle is misled by the traffic light on the track, stopping in the middle of the road. So the question is, can we anticipate this before it happens? And we explore the idea of using a general purpose open vocabulary object detector to parse the scene, which finds, among other detections, that the truck carrying a traffic light is part of the scene. And we use this information with an input prop template. You can see that it's quite long, it's shown here on the right. And this template incorporates various best practices, including warming up the large language model with a few reasoning examples for detecting semantic anomalies. We then receive an output where the large language model has assessed the scene contents, deeming some objects such as trees or street lights to be no cause for alarm, but indicating indeed that the truck carrying a traffic light is an anomaly worth flagging. In addition to classifying these scenarios as anomalous, the large language models also hypothesizes the way it could negatively impact the policy behavior of the AV, which is very, very interesting and remarkable. So specifically, bullet point number 3, at the question, can the vehicle drive safely in its presence, and the bottom left? The answer of the LLM is no, this could deceive the vehicle into interpreting the traffic light as a legal traffic signal, which is quite remarkable. So we've also used this methodology successfully in a robotic manipulation context, as well as other driving scenarios. But of course, this is just a start. First, it's notable that large language models are able to recognize the root causes of common semantic errors, but we also notice that they sometimes hallucinate possible sources of confusion. So an important next step is to ground the large language model on the capabilities of the autonomy stack, for example, as determined by the design specification, in order to limit the possibility of hallucinations. On the other hand, LLM hallucinations are not necessarily bad. Researchers and practitioners are already using such foundation models for data augmentation. And I do believe that the large language model postulated source of semantic confusion, which are indeed plausible extrapolations of the training dataset, may be extremely useful for iteration and validation, basically generating edge cases that really have a semantic semantic feature that really stress test an AV stack. Third, in the example that I provided, we use a vision transformer to convert an image of the scene into a format amenable to an LLM input. But this might induce information losses. A picture is really worth 1,000 tokens, if not more. Luckily, on the horizon are multimodal language models. That is, models that can take images directly as input and may allow us to sidestep the scene description step entirely. And finally, I view such semantic anomaly detectors as fully complementary to other low-level runtime monitors that we have been investigating in my lab, and also other people have been developing in the past. And we plan to explore best ways to combine these different ideas in a sort of hierarchical framework for anomaly detection. So in conclusion, there is clearly no silver bullet to enable trusted AI for autonomous vehicle. That's why we are pursuing several complementary directions. And here today, I particularly highlighted our work on simulation and the semantic anomaly detection. With that, thank you for your attention. And of course, I would like to acknowledge all my collaborators, both at Stanford and Nvidia.
Hey, great, thanks. It's an excellent talk for Michael. So I have the questions. So I give the opportunity for the people in the room first.
Thank you for that wonderful presentation. My question would be inspired by the previous presentation, where they tried to predict the intention of surrounding agents whenever a vehicle or the eco-vehicle is making lane change, for example. Could you see that the approach that you proposed being used to predict the intention of other agents as well?
Yeah, unfortunately, I couldn't hear the question very well. Would you mind repeating it?
Sorry.
The sound was a little bit broken.
Could you try that again?
Sure.
Just say once, just check.
Can you hear me now?
Oh, if it is in the chat, I can also read the chat. So let me. Yeah, unfortunately.
Can you hear me now?
Yes.
Let's see. Check. Can you hear us, Marco?
Yes. Now I can hear you. Yep.
Okay. Yeah.
Perfect. Yeah. So thank you for the presentation. This was wonderful. My question is inspired by the previous presentation. So they tried to predict the intention of surrounding agents whenever performing a maneuver. So could you see the approach that you proposed, specifically using the chain of thought to predict the intention of surrounding agents as well?
Yeah, that's a good question. Yeah, I think so. So it's kind of interesting that so we went from prediction then to simulation, and then we're using large language models to aid in basically building traffic models. But something that we haven't done is actually to then close the loop and use some of the chain of thought reasoning capabilities displayed by an LLM to boost the predictive performance of trajectory forecasting models, especially beyond, say, a couple of seconds horizon. So I think it's possible and promising. We haven't worked on it, but I think it's a good idea.
Thank you.
Okay, other questions? Sorry, I'm over.
Hi, thank you for the very interesting talk. And I have a question about your LLM for anomaly detection. So my question is, do you use any metrics to quantify whether a scenario is anomaly? And do you use the metrics to quantify that your reasoning is good or not? Because your case showing that there's a traffic light on track, it is obviously very anomaly, but the case like a stop sign on a billboard, it's kind of not that anomaly, right? So yeah, so my question is whether there's a metric to quantify such kind of thing.
Yeah, I mean, it's a very important question and a very difficult one with many facets. So in the case of a billboard, it's indeed quite anomalous, and actually that is a real case taken from Tesla driving law. So what happened with that stop sign is that repeatedly Tesla vehicles were stopping at that billboard, interpreting the stop sign as a real one, thereby causing ghost brakes. And ghost brakes, so basically braking for no apparent reason, not only are an inconvenience, of course, it's very annoying for the person on board, but at the same time, they are a safety hazard because they can be rear-ended. As you said, from the point of view of the detector, that was not really an anomaly. The stop sign was actually an in-distribution object, but the context of it makes it an anomaly, and that's what basically an LLM allows us to measure and to detect. So if you will, for us, the LLM is the measure that allows us to go beyond the pure object level anomaly detection metrics into something that is more contextual. But as I said, this is just a start. Sometimes the LLM can hallucinate some sources of confusion, so they might think that some context making in distribution object anomalous and worth plugging when that is not the case. So I think there is tons more work to do there. So I hope that this answers your question.
Great. Any other questions? You can line up here if you have questions.
Yes, thanks, Marco, for the great talk, and it's very inspiring. Yeah, so my question is about like kind of related to the previous question, but in the text of prediction and the scene generation, like you just mentioned, like you can use the prediction model to generate diverse and many different scenarios. But my question is like, how do you quantify the data distribution in the scenario generation? Like we have so many factors in the scene, like different geometry, different cars, maybe cars may have different driving styles and different type. So any ideas like to how to quantify the distribution of the scenario generation?
Yeah, another great question. So first of all, we do not really use prediction models directly in order to build the traffic models, because as I've argued, so if you just close the loop on a prediction model, so you let vehicles drive their own predictions, say for the first 1 second, and then you recompute based on what other people do, very quickly you get out of distribution, the model diverges, and then the output becomes erratic. So that's why we have developed some refinement to this idea, exploiting, for example, a hierarchical imitation learning approach in order to robustify the model and thereby enabling long horizon simulation. But coming to your question, as I was arguing, there is no real metric that allows us to understand whether our data set is large enough to cover all the scenes we are interested in, let alone whether our model that is learned on that data set is good enough to cover, all the things that you care about. So that's why we have a plethora of metrics, from a more geometric one that look at how varied the trajectories are from each other, or what are the distributions of low-level quantities like speed and jerk, all the way to human likeness scores. So that's on the metric side. On the generating new and interesting scenes, well, that's why we are embracing a generative AI approach that hopefully allow us to generate new content. But at the same time, to go even beyond, that's exactly why we plan at looking at LLM hallucinations to give us an additional boost in terms of new tricky scenes that we can generate. So beyond, for example, those that are captured by text, for example, police reports or YouTube videos, or all the sources that you have out there, using the LLM itself to create even new ones. So this is going to be something that is going to be with us for the next several years. But I think by now we have good tools in order to create scenarios that are increasingly more complicated, increasingly more in detail. So I hope this helps. It's not a very crisp answer, but because, of course, the topic is very, very difficult and has many different facets.
Yeah, thanks. I think that it's exciting introduction. Like we have a very good beginning to work on that action. Yeah, thanks for the answer.
And I
Okay,
think this
so let's
foundation
answer.
model,
Sorry, go ahead.
no, what I was saying is that they're quite awful that actually these foundation models allow us to reason very meaningfully about detail. You don't need, because basically they unlock as a data source, not just driving logs that are expensive to get, but many other sources. I mean, many corner cases, they go beyond the driving and they can be learned directly from videos that you can randomly find on the internet. So I think that's very promising. Of course, a lot of work to do.
Okay, great. Thanks, speaker. Okay, thank you, Michael.
Yeah, thank you very much for having me. And
okay.
Sorry for not being there in person.
Okay, yeah, okay. See you. So we'll have a half an hour coffee break and we'll come back at 11. Thank you. Good. Okay. Hi, everyone. So we'll continue with our speaker in this section. So our next speaker is Professor Bole Zhou. Bole is assistant professor at CS at UCLA. He studies interpretable human-AI interaction for human vision and machine autonomy. So he's also interested in understanding various human-centric properties of current AI models beyond their accuracy, such as explainability, interpretability, steerability, generalizability, and safety. So without further delay, please, you can start.
Yes, thank you for the introduction, and thank you for coming. Yeah, I'm very glad to be here. So I'm trained as a computer vision researcher, but in recent 3 years, we start doing a lot of research on machine autonomy. Basically, we try to combine machine perception with autonomy together, build this end-to-end agent that can explore and interact with the real world. Today, I would like to share with you some of our research on this AI safety, like how can we generate and simulate real-world traffic scenarios to evaluate and improve AI safety. So AI safety for sure is a very important issue for the real-world deployment of autonomy system, right? So in real world, so there are a lot of complex situations. So it's hard to know whether this autonomous agent trained from some large-scale trainings can react safely and reliably. So then we have to thoroughly evaluate their performance. So one very typical setting is that we will evaluate the AI safety in simulation before their real-world deployments. So over the years, so we developed many open source simulation tools that facilitates the research in this direction. Those simulators ranging from this video games to the Scala and to recent Nvidia developed this drive sim based on Isaka Jim has very realistic visual renderings. But given those wonderful simulators, there are still a lot of issues. So one critical issue is that most of the existing simulators focus on the perception parts. But for this autonomous system, so this driving stack is have so many different components ranging from perception to later decision, planning, and control. Right, so then our simulator right now, it just improve the perception part, like how can we simulate this visual appearance of the traffic scenarios. But all the later parts, the downstream part, like decision planning control, is left underexplored. So we want to develop better tools to facilitate the research in this AI decision. Also empower the academic communities work on those problems. Also, there are some other limitations, such as existing simulator use a fixed asset and maps. So usually they will train and evaluate on the similar maps, which lead to this overfitting issues. So it's really hard to evaluate the performance of the agent on those limited number of assets. Also, simulators using oversimplified scenarios. So it's hard to see how this agent will perform in this wide range of scenarios. So to improve these issues, along with my student, we are on the efforts of developing new open source driving simulator called MetaDrive. So one key design of this MetaDrive open source simulator is that we have a data-driven scenario design. So it's very flexible to input the real data as well as learning to generate new ones. Also, this MetaDrive have very high efficiency and very lightweight, so you can run more than 500 FPS on a standard PC. So also based on MetaDrive, we build a range of learning tasks and then benchmarks from safe reinforcement learning to multi-agent reinforcement learning and more. So this MetaDrive already open source as this link. So here is one function inside MetaDrive that allow us to generate infinite number of scenarios. So we first define the elementary traffic blocks. Then we can follow the procedure generation and then randomly sample from the predefined traffic assets. Then we can glue them together into a map and then turn those maps into the interactive environments. So we can use this newly created environment for training as well as testing for the agent inside the environment. We also built the benchmark for safe reinforcement learning. In reinforcement learning community, this safe IO is a problem that we want to minimize the cost while learn the policy. So then we can design new safe IO algorithms. So here is a demonstration of the agent during the training. So you can see this agent trained from reinforcement learning. Then this agent are making a lot of mistakes in order to pick up the right driving behavior. So here we have a cost here. Then after trainings, and then this agent can have a high safety performance. So here is the agent after training with safe reinforcement learning inside the environment, then it can have a very excellent driving capabilities. So this agent is trained from this reinforcement learning from scratch. This agent even can figure out the shortcuts between two traffic cones, and yeah. So based on MetaDrive, we also built some other interesting benchmark, such as this multi-agent reinforcement learning. So previously, when people develop multi-agent reinforcement learning, so they will evaluate on some like video games, StarCraft. So it's not so realistic. So we can using those different traffic scenario and environments to develop the multi-agent reinforcement learning. So each vehicle is controlled by an independent policy. So they will learn to coordinate with each other. Then people can also evaluate different multi-agent IO algorithm. We also developed some multi-agent algorithm called coordinated policy optimization. So we have two levels of coordination. So one is at the local coordination level, another is at global coordination. Then we benchmark with other multi-agent algorithms and show we can improve the prior method. More interestingly, there are some emergent collective behaviors. So you can see here, I show you after training, although the reward function is just the maximize population rewards, then some vehicles have this emergent collective behavior. So they learn to yield to other vehicles. Also some vehicle yield learn how to compete and cut in other vehicles. So we can study the agent behaviors, different collective motions using this benchmark. For recent 6 months, we are keeping improving this MetaDrive. So we are on the pathway towards MetaDriverse. So I'll tell you that as a metaverse of driving environments. So we want to have a data-driven system design. So then we have this 3 layers of design for this MetaDrivers. We first have the data layer, which allow people to input different open source data sets released by different autonomous driving companies. So here we can incorporate data sets released by Waymo, New Plan, New Things, and also Level 5, and many other data sets. So we provide the data APIs, allow people to input different resources. Then we have the system layers that we can incorporate this heterogeneous data set into the unified format and allow people to have a lot of functions to control the scenarios. We further have the application layer that supports a range of applications. So people also can add their own application at this layer. So we already have the single agent learning, multi-agent learning, scenario generation, and even this autonomous driving stack testing functions. So here is a demonstration video of the meta drivers. We largely improved the visual rendering parts of the meta drive. So here is a scenes from new scenes data set. So we can input the driving logs and recreate the simulated environment inside our simulator. We also can provide multiple sensor inputs ranging from depths to RGB to LiDARs, so allow people to study different problems like sensor fusions and from perception to also autonomy applications. So here another. So based on meta drivers, we are also collecting a large-scale repository of real-world scenarios. Because we unify the format, and then we can input the scenarios from all the other driving data sets. So here is a demo video showing you the collected scenarios. So we have right now we have more than 500,000 real-world traffic scenarios imported from different data sets. Waymo, a new plan. We also can have the procedurally generated scenarios. So based on this large-scale data, then we can study many different problems, such as AI safety and also many other like neural rendering tasks and also decision-making tasks using those data. So we will make the data and code available through this link called ScenarioNet. Here is another demo video showing you the synchronized simulation between the real world and the simulated world. So basically, we input the driving video or driving logs from new scenes data sets. Then we use their bounding box and the HD map to reconstruct the traffic scenarios inside our driving simulator. So we both have this 3D rendering as well as a top-down view of the scenarios. Because we can input many scenarios from different data sets, then we can have a systematic analysis on those traffic scenarios. So here is a plot of a t-SNE visualization of the imported scenarios. So each scenario is embedded using an encoder of a traffic generation model called traffic gen. So I will introduce this later. Basically, for each scenario, so we can extract their embedding features. Then we treat each scenario then as a embedding. Then we can build a t-SNE visualization. Then we can use a t-SNE visualization to analyze the similarity and the differences across different data sets. So these embeddings contain scenarios from Waymo, new plan, and the procedure generation. Then you can see there is a clear difference between the procedurally generated scenarios and the real-world scenarios. Also, there are some difference between the Waymo dataset and the new plan datasets. On the lower right corner, then you can see Waymo dataset have more complex intersections. They have the scenarios with multiple lengths compared to the new plan. They have more limited number of lengths. I think one issue is for new plans. So many of the scenarios in new plan are collected in Singapore. So it's a small city country, so they don't have this so many lengths. So that allow us to analyze the similarity and difference of the scenarios. We also built this AD stack testing function, which allow people to plug their AD stack and evaluate those AD stack using the traffic scenarios. So we have the bridge to ROS interface. So ROS is a very widely used robotics platform. Then we can replace the scenarios in ROS. We also bridge meta drivers with this OpenPilot AT stack. So OpenPilot is an open source driving stack where you can just mount a camera in front of the dashboard. Then wear this OpenPilot software with your vehicle, then you can have this basic autonomous driving capabilities. So we just input this OpenPilot inside this MetaDriver simulator. Then we can evaluate the OpenPilot AD stack directly inside this simulators. So here is this demo video showing you, here we are running this OpenPilot AD stack inside our simulator. So they have this basic land following capabilities. Although there are some domain gap between the visual rendering from the simulators and the real world. So this allows us to test the performance of the AD stack. So we provide a lot of APIs to allow people to also customize their own AD stack and evaluate that on our imported scenarios. We also have the user interface. I think that is a missing part for most of the driving simulators, because so we can have the user interface, then we can study many interesting problems on this human vehicle interactions. So here is a demo video showing you how human can using the joystick to interact and drive inside simulator, like playing a video game. Then we can simulate a lot of traffic scenarios or safety critical scenarios and study how human drivers will react to those challenging scenarios. Next, I would like to give you a case study on how can we use the scenarios to do some machine learning applications. So here we want to learn to generate diverse and realistic traffic scenarios. One issue we noticed is that a lot of the real world scenarios are very noisy and fragmented, right? So those trajectories are very short, then it's hard to use this directly for evaluation. So what we want to do is we want to train generative AI models on the noisy and the fragmented scenario data. Then we can sample from the training the generative models and generate more complete scenario data. So then we develop generative models called traffic gen. So this model follow an encoder and decoder design. So it has a two-stage generation process. So stage one, we will train the model to place the vehicle on the input HD map. So we'll learn to place each vehicle autoregressively on the input HD map. Then we have a second stage that generates the trajectories for each vehicles by leveraging this motion forecasting models. So here is a generation process. So you can see this heat map will indicate what is the next likely locations for the vehicle, and we'll place the vehicle inside. Then we will generate the vehicle's future trajectories. Then we can then input this generated scenarios inside our simulator and simulate those generated scenarios. So this work it's published at the ICRA this year. We also open source this traffic gen code base. So here are some of the demos. So here we can generate different traffic flows on different maps. So here are all the generated traffic behaviors. Now you can see we even can control the traffic lights, then use the traffic light to control the traffic behaviors. Also for the same map, so we can randomize the generation process and generate the different traffic flows on the same map. This generative AI models have other applications. For example, we can use this model to edit the existing real-world scenarios. For example, here we have the real-world scenarios. Then we can use a model to extend their trajectories. Also for some real world scenarios, so it's very sparse, then we want to increase the difficulties of the scenarios, then we can use a model to place more vehicle inside the HD map, then we can make the things more challenging to the agent to train and evaluate. So then we conduct some quantitative experiments and evaluate how can we use generated scenarios to improve the driving policy. So here we have an experiment driving policy trained from the reinforcement learning algorithm PPO. So we train on procedurally generated data. Then there is a clear gap between the successful rates on the real world test sets and the model trained on generated data. So if we train this agent using the synthetic data sampled from the traffic gen, then we can recover the performance, which means the training set of the synthetic data is very similar to the real data distributions. With further augmentation, for example, we can intentionally sample from the tail distribution, then we can generate more challenging cases and use them as a training data. Then we can further improve the safety of the training policy. So we can decrease the safety violations to 2.14. So this traffic gen also can be adapted in other simulators. So we are developing this bridge to other simulators. For example, the other simulator, Color and the GTA 5, they have their own HD map. Then we can just use their own HD map and apply our traffic gen on this vectorized representation. Then we can generate more diverse scenarios and input those scenarios inside other driving simulators. So here are some of the results we have by transferring the traffic gen scenarios to other simulators. So here is an intersection in Color. So I show you 3 generated scenario by traffic gen and imported into the Color environment. So here another one for the same intersection. We can generate the diverse traffic scenarios. So it's not perfect. Sometimes these data-driven models make some mistake. Here on the lower right corner, then you can see they generate some vehicles opposite with each other. So that violates this traffic rules. So there are still some improvement space to improve this data-driven generative models. We still noticed there are some issues with the generative model. One fundamental issue is that here we are using a machine learning model, right? So, but the machine learning model have the things that they will just learn the overall data distribution. But if you sample from this generative model, this machine learning model, then you will get the most probable scenarios. So those scenarios are usually normal scenarios. So it's hard to sample this challenging or safety critical scenarios. So because safety critical scenarios are pretty rare and extremely valuable to do the stream test. So here is a plot from a survey written by Professor Ding's group. So those safety critical scenarios are always at the tail, right? So it's then very difficult to directly sample those safety critical scenarios from those knowledge generative AI models. And we have to explore other ways to generate the safety critical scenarios as a corner case. So we have a recent effort try to develop some adversarial training pipeline to generate and train with the safety critical scenarios. So starting from the scenario dataset, then we can sample normal traffic scenarios, right? Because in real world, most of the collected scenarios are just normal traffic scenarios. Then we design some mechanism that can do the safety critical resampling. So giving this normal traffic scenarios, we can do some resampling, then we can generate the adversarial traffic scenarios. Then we that have some extant poor behaviors inside the traffic scenario. Then we can use this generated scenarios to train this driving policy. Then we can close the loop for this training. Then we have this closed loop adversarial training. So it's similar to this adversarial training for this adversarial samples. But here we generate this physically plausible safety critical scenarios. So for this safety critical resampling, we model this safety critical scenario generation as a Bayesian sampling process. So basically giving this normal scenarios, we utilize a knowledge motion prediction model to generate the future possible trajectories. So that can allow us to generate realistic trajectories. Right. So giving this generated all the possible future trajectories for the opponent vehicles, then we can sample the trajectories that most adversarial to the ego vehicle. Then, so through this kind of resampling, we can both ensure the realism and the safety critical score of the generated scenarios. So for the generated scenario, we evaluate their performance. So here we evaluate how this safety critical scenarios affect the agents. So here we select 2 agents. So one is an IBM controlled agent, and also we have a pre-trained reinforcement learning agent. Then we compare with the prior method, the Strive method, and see how the performance or the occlusion rates will increase when we apply the safety critical scenario generation. So we can outperform Strive on this. And also more importantly, our sample efficiency is very high because for Strive is the iterative process. So it's very slow to run. So it's hard to use Strive to generate a large number of training samples. But for our methods, it has very high sample efficiency. Then we can include this into the training loop, then use the generated scenarios on the fly to improve the agent. So we further show that this generated samples can further improve the AI safety of the driving policy. So we compare with the method with the data using just the replay, and also use the open loop generation. Like you generate a ton of safety critical samples beforehand, then use this to add a training sample. Then we show this kind of closed loop adversarial training with safety critical scenarios can improve the safeties as a testing time. So we plan to release a code and paper very soon through this repo. So you are welcome to follow this repo to get the latest updates. So here are some of the generated samples for the on the left is normal scenarios. So after the adversarial generations resampling, then we can generate this safety critical scenarios. Let's see here, this car just turning, then affect this ego vehicle. Another scenarios. We should merge and affect this ego vehicle, right? So now we can generate the safety critical behaviors. Then we can use those generated samples as a stress test for the agent, as well as use as a training sample to improve its performance in the simulation. Furthermore, I would like to just highlight some of the CVPR paper we have at here. So here is a work called the V2V4 Real. So we build a large-scale real-world data sets for vehicle-to-vehicle cooperative perception. Existing driving data set usually just collected by one single vehicles driving around, right? So for this data set, we have like two vehicles that are connected to each other and collect the data inside the real traffic scenes. So this is a collaboration project with UCLA Mobility Lab, led by Professor Jachima. So here is a demo video showing you the vehicles. So we collect, so two vehicles are collecting data together. Then we synchronize their perceptions, and we can study how this vehicle can share their perception and create this cooperative perception to improve the AI safety. Okay, so I would like to stop here. So we are building this meta drivers as an open source research platform to facilitate the AI and autonomy research. So we release all the paper, code, and simulator as this meta drivers GitHub then I'll link. So this project is supported by NSF, Samsung, and Cisco, and also developed by many of my students. Okay, so I'm happy to answer any questions.
Great. I think it's very impressive. Actually, our group also use MetaDrive a lot. It's a really big contribution to the community. So any questions from the audience in the room? And also on people online, you feel free to ask questions directly or post questions on the chat. So there are one question. So there are different notions of AV driving safety, technical V2 verification and validation. In traffic, etc., which safety notion do you think the simulator-based evaluation strategy are focusing on?
Yeah, that's a great question. So I totally agree with you. So there are multiple levels of AI safety. So for the AI safety we study here is about the behavior safety. So we want to study how the agent will react to the adversarial driving behaviors from other opponent vehicles.
Yeah, kind of picking up on one of the talks earlier, there's sort of this range between kind of a fully cooperative and a fully adversarial. And if you have, fully adversarial trying to, hit you, then it's very difficult to drive. As you're thinking about adversarial example, like how do you think about kind of that primarization, just to understand sort of how adversarial to kind of get those interesting ones that aren't actually just collisions?
I see. Yeah, that's a great question. I think in traffic scenarios, actually people try to avoid accident, right? Not people want cause accidents, but it's just the accidental behaviors will lead to the collisions. I think in our simulator, we try to have the control over this. Like if you can have some parameter like control the cooperation level as well as adversarial levels, then we can create more diverse traffic scenarios, safety critical scenarios, and test the agent. So I think so it's great to have more control on this generation process to control this cooperative and adversarialness of the behaviors.
Well, thanks for your talk. And we always say for a foundation model, what we need is not raw data, but more useful and accurate data. So I want to know, how do you verify the safety of your system when transferring from simulators to open world scenarios, and how to fill the gap in those two fields?
Yeah, that's a great question. So there are always a gap between the simulation and the real world. So what we are doing here is try to borrow more asset from real world, right? So because previous simulator, they only have limited number of traffic scenarios. So we also work on the simplified road structure. So we have this effort, like try to input more traffic scenarios. Like I show you, we have 500,000 different traffic scenarios. So when we evaluate against so many traffic scenarios, so hopefully we can narrow the gap. Like how can we bridge the gap? I think it's an open problem. How can we really like bridge the gap?
Thank you. Another question is that I want to know the details about the ability of scaling up with less hassle.
You mean the scalability of the training?
Of the scaling up to get more scenarios for the simulation.
I see. Yeah, I think right now we try to input more traffic scenarios, but still not enough. That's why we have the generative AI, also like Mark from Stanford. He also demonstrate we can use generative AI to generate more diverse scenarios, because many of the safety critical scenarios, it's hard to collect in real world. Then we have to synthesize using multiple ways. Could be using this adversarial training, or could be using the large language model to generate the scenarios.
Okay, thank you very much.
Yeah, thank you.
Thank you for the very great talk. And since we are talking about safety and about communities, so I have a little bit nitpicking question. So from my understanding, that you generate from public datasets and import the dataset into the simulator, right? So my question is like, because in the real world dataset, there are many like trees or buildings on the street, but in the simulator, they are gone. So I was wondering whether you have studied like the impact of such kind of events.
Yeah, that's a great question. So then you notice that in our simulator, we don't have building and the trees. So we are improving that. So we try to use some neural renderings to include more traffic background inside this. Then we can also study the interaction between the buildings and the trees with traffic flows. Yeah, so we want to improve the realism of the simulators using some neural rendering techniques.
Okay, so let's thank our speaker.
Yeah, thank you.
Thank you. Okay, so we'll have our poster session. So you can put your poster on the board at the end of the room. And then we'll have a half an hour post session until noon. And then after that, we'll have a lunch break. We'll come back to this room at 2 p.m. And we have another few speakers. So thanks for attending. Okay, hello everyone. So we will start our afternoon session with Alexandra Patrick. So Alexandra is a technical lead manager at Neuro, leading the applied machine learning research. He's also a lecturer at Lomonosov Moscow State University, giving courses on theory of deep learning. So he received his master and PhD in theoretical computer science. Before Neuro, he worked as a principal engineer at Huawei as managing director, leading research at Artificial Intelligence Research Institute, organized and led collaboration activities between academia and the industry. I think his research interest lies in the application of empirical and theoretical robustness technologies to different practical tasks, and related work has been published on top venues. So welcome, Alexandra.
Thank you for the invitation. I'm really excited to be here and to be invited here by the organizers. And it seems like it's been a while since Neuro has presented anything. So today I'm trying to pour some light on the technical part of the research that we are doing inside. I'm a little bit sad that we are not sharing anything about perception and anything about computer vision, although we are here at computer vision conference. But as we are on the safety workshop, so I will share something about how we will tackle the safety problem. Today's talk will be about the behavior model and learned motion selection for safe driving. Yeah, let me start. To be honest, this is not my work. This is the work of the whole and big team. The main contributors here are Wei, Jonathan Nash, and Władysław and Jin Lee, and many, many others. And let's start. What problems we would like to overcome and would like to solve? First of all, when we're talking about other agents on the road, we would like to have some really trustworthy predictions for them, and to use it both from both points of view. First of all, in terms of prediction when we're talking about autonomy, and second, how to use them inside simulations. Second, this is when we are considering our ego motion and plans. We would like to have the really reliable motion selection in order to work on top of different sources of ego plans. It could be heuristic plans, it could be recovery plans, it could be plans provided by different ML models. So, and we need to select which one to use. And the approach that we are right now doing inside our team is to use better training, evaluation, and reasoning, leading to eventually to safer driving. Okay. First, let's start with the problem of agents. And the problem, this is when we are using the imitation learning-based prediction model for other agents, it could lead us to really unreasonable proposals because of distribution shift. And I think most of you can understand that we usually cannot use it in closed-loop simulation. And the historical approach is just to use heuristic-based models for closed-loop simulation. But what if you would like to concentrate more and more on machine learning-based approaches? And this is our solution, where we would like to target models with better coverage of distributions. And at the same time, we are not only going to use it inside simulation, but at the same time, we would like to reuse it in the autonomy stack for predictions. And this is a little bit different problems, but we would like to kill two birds by one stone. Yeah, and what about ego motion? And the problem here is that decisions are here really have delayed consequences. They are really long term. And historically, we could do it by, for example, using long-term machine learning-based predictions. but again, the more long-term horizon we use, the less reliable these predictions are. And our solution here is to learn a specific machine learning-based model that takes into account the expectation of all features. And this is how we can narrow down the search space. We are not doing the planning itself by our model, we are just select. Okay, let's start with other agents. And here we are using diffusion model. Some background, I think, you know, with diffusion models, we have forward process, reverse process, diffusion analogy. So we are jumping from X T capital to the, this is usually the white noise, into the X0, which is denoised input. This is what we would like to have. We would like to have these denoisers. And right now, everyone knows about the current success of diffusion models. Mostly this is connected to the text-to-image tasks like Google Image Gen, OpenAI and DALL-E 2, and Midjourney. Also, we can do the same visualization for video generation, audio generation, etc. So it seems like the generation for these tasks mostly done, at least done in a good way. And sorry, GANs, which dominated probably like 5 years ago, etc. But what about other tasks, especially when we're talking about autonomy? Yeah. For example, we could use it for controllable traffic generation or CTG. This is what today in the morning Marco talked about for traffic simulation. And or, for example, the latest paper from Waymo called Motion Diffuser, when we are trying to do the joint prediction. That's nice. And it seems that we are trying to combine both functionalities of these models. We would like to have reliable predictions and good simulation at the same time. And I could be a little bit sad, for example, why we are not publishing in advance, because we started to do this work even before any of these papers appeared, to be honest. But this is quite good for our team because we are applied machine learning research, and this is sort of justifications for what we are doing is very interesting and important for other academia and industry, and sort of proof of concept what we are doing. Okay, when we're talking about the diffusion models, what we would like to have here. First of all, the development of a trajectory generation model that can capture the distribution. Second, yeah, we would like to improve the simulations, the closed-loop simulations. And the model which we called diffusion-based trajectory generator, or DTG, as you can see, very similar to CTG from from Nvidia and from the papers that Marco today talked about. When we're talking about the coverage of distribution, this is why it is beneficial to use diffusion-based models, because it is theoretically ensured and justified by variational diffusion models, where we explicitly optimize elbow, variance lower bound. And if we have reliable closed-loop simulation, we could use it not only for eval of our systems, but also for reinforcement learning-based trainings. What the features we would like to pursue? First of all, to learn diverse behavior with distribution that matches real-world driver behaviors. Second, provide good prediction metrics like mean ADE, NLL, and others. And second, or third one is to lead to stable and consistent simulation. This is our current, probably a little bit outdated, but still very similar to what we have right now in terms of architecture for DTG. So we have encoder. Encoder can be different. Input for the encoder is a context map, HD map. Also, we are using the history of other agents. any encoder can be used. Then we have context embeddings. Then we also have noisy trajectory candidates. As for diffusion models, we really needed, so we added some noise levels and concatenated and used some decoder. It could be MLP, it could be transformer-based again. And we used an energy-based formulation. And that's why how we can use it. And as I said, for VDM, we have a good distribution coverage, but we also need some good prediction metrics. How we can do it? We can do it by sampling multiple trajectories and then classification. So, for example, you can see here the, I don't know, very dense predictions. It's 128 predictions. And when they classify them, we can see much more clear picture here. Okay, let's jump into the ego motion. Here a little bit of background in terms of array. I think that's quite obvious. So for optimization process, we need objectives. We need some process to learn, and what we need to optimize. We mostly looking into the offline of policy, not offline. And let me, just the problem itself. So usually we have a very sparse reward. It could be like, I don't know, 1 over like 100 of steps or even less. And what we are doing for motion selection and why we are doing motion selection. First of all, motion selection is a simpler problem than just doing this using array as a planner, because we have discrete and very, I don't know, small number of trajectories. And we would like to rank the trajectories rather than produce them. And why it is? Because we have multiple sources of trajectories. It could be imitation learning-based planners. It could be heuristic-based planners. It could be like some recovery-based planners. Yes, and they already existed. They already provide a quite good trajectory. So you just need some time to understand which one to use. And this is done internally by so-called RLMS, RL for motion selection. Yeah, this is how we can allow heuristics and domain knowledge to be used. Yeah, usual array settings. We have policy, we have value, we have for action. Action here is the trajectory itself. Policy is which trajectory to use, and value how good this trajectory. And what we are using, we're using the dense Q values, like vectorized one, like reward 1, reward 2, reward 3, etc. It could be, for example, some distance traveled and any other values that you would like to maximize. Problem here is that we do not have concrete notion or constraint on safety, and here we are because of safety. Yeah, the initial step here, how to overcome this problem, is to use risk-sensitive RL. So we're adding additional stream, it's called risk, and we have Q risk values. And here we would like to probably to minimize them, not to maximize. Yeah, and we are also using the sparse rewards, which mostly like risks here, risk 1, risk 2, and risk 3. Probably, for example, it could be collision, rate of collision, for example. And we still do not have the hard constraint here. So we need to add something additional, and here we're adding the recovery policy. And the very simple diagram here can be depicted as the following. So during the inference, we have some Q risk values, and we need to compare with some threshold. And if it's safe, or for example, if it's less than some thresholds, we are using usual our task policy invoking, or if it's not so, we need to refer to some failover policy. And this is one additional image of how it could be done. So we are just having the state, we are having the action, and we would like to understand whether it's safe or not to invoke the specific action, to use this action. If it's the Q risk value of it, if more than some predefined threshold epsilon risk, it means that we are unsafe, and we are just executing a recovery policy. If it's not, then we execute a usual our learn task policy. Yeah, and very simple diagrams. So we first executing our current RLMS policy is a simulator and storing trajectories in some replay buffer. Then we are making these transitions. Using these trajectories, we need to train the task critic and risk critics here. We have dense rewards, dense risks. Then we are combining them using like some weighted average into the utils, and then train policies for each. And the last part here remaining, this is how to combine task recovery policy to get the overall RLMS policy. And this is done quite interestingly. So as we already saw that we have multiple risks and we have multiple actions, these multiple trajectories, and we can see that some of them are below thresholds, and if they are below thresholds, they are green. And here we have the A1, A2, and A3 are safe trajectories. So we then renormalize the task policy and just using this task policy to sample. But if, for example, all at some of the risk values, if all trajectories are unsafe, so we need to invoke recovery policy here. So we have everything on our plate. We have different key values for risks and for tasks. Also, we have a recovery policy and we have a usual task policy. So this is how the overall framework of recovery RL can be used and how it's used internally. And let's go to some examples. For example, when we're talking about the diffusion-based trajectory generator, it really can provide us some good and reasonable things that wasn't captured in the ground truth. For example, here we have dashed red is the history and solid red is the ground truth future. Blue one is map and green one are predictions. And you can see here that prediction can turn right while ground truth is just straight. And we can see here even like some lane changes. Here again, we can see potential lane change when ground truth is just going straight. And quite interesting case, we have the uncertain cyclists. And when we're talking about cyclists and pedestrians, they are very uncertain. They can go like literally everywhere on the map. And the diffusion-based model really captures this uncertainty. Yeah, some additional examples about RLMS, and here just closed loop simulation. On the top row, we have on road log, and the bottom one, the simulation based. And here we can see that RLMS doing well while dealing with vehicle overtaken near a bottom on the left. So you can be seen on the bottom row here. Just yielding a little bit. Another one example here is occluded unprotected left. And again, on the top on road log and the bottom simulated one. And we can see that it is dealing quite well, just yielding a little bit in the beginning and then go through the intersection. And last one example that just providing not every situation is, how to say, can be tackled by the RLMS. Sometimes we have the problems and the problems with stability because selection itself can be a combination of plans. And sometimes we just do not have inside our source of different plans, just a single and good plan that can be pursued towards the whole, I don't know, the scene. So we need to concatenate multiple plans, and this is how we create the new one. And this is sort of instability. And sometimes, for example, here we are just doing an unreasonable yield. For example, on the top row, we already turned right, but at the bottom row, we are still creeping a little bit. So that's the issue, and we are working on it. Some more limitations of the DTG. Diffusion-based model having some problems because it's sampling only inference and it's hard to use in the production. Also, there are multiple ways how to overcome this problem just by distillation or some others. This is a trade-off. And yeah, for example, by doing this distillation, we can lose some theoretical guarantees, unfortunately. The second one is a latency performance trade-off. That is this the coincidence of the first one. Because on the road, usually on board, we don't have much compute power, and we need to sacrifice some of the I don't know, performance here. And the third one, and here I'm not sure whether it's a bug or feature, we have non-deterministic simulation because we really need to sample. And sometimes we just don't need to be bit exact every time. Sometimes we need. So it's dependent on the specific usage of simulation. But there are ways how we can overcome it by, for example, using specific ways of conditioning. When we're talking about RLMS, we still do not have the hard constraint on safety. What we have seen today, it was sort of more soft constraints on safety, although it's like a quite well-established framework. It's still not providing 100% of guarantee here. We still need to work here. The second one, we have this problem for sparse events, and we are still challenging to learn, like collisions, multiple mitigations, but not the single solution. And yes, as always, when we're talking about RL, this is sample inefficient. It's really many simulation steps to learn, probably with, I don't know, foundational model, especially, for example, for autonomy and especially for RL, can be solved to some extent, but right now we don't have it, so it's still a problem. The conclusions, when we're talking about diffusion-based models, they help to measure distributions, not the points. And this is really important because sometimes we don't have the explicit future. Sometimes we can have a variety of different futures. And what we need to cover the human-like behavior, not to be like explicitly 100% the same. And diffusion-based models at the same time can be justified by theoretical guarantees in comparison to imitation learning based, for example. The second, when we're talking about RL motion selection, we learning selection, and this selection provides us long horizon reasoning. And this is very important because we much more, how to say, more suited to be used inside closed loop in comparison to just open loop and just I don't know, predictions which we can use only in the open loop settings. And yeah, the last one, last but not the least, that recent academic state of the art really can be used for practical tasks, and we can, as we could see, we can do it in parallel, different like ways of research, and at the same time we can converse it like internally and externally, and in order to eventually to provide much more safety than we have right now. Yep, join us, our ML team. Thank you.
Any questions? Okay, so I have a question for. I think it's very interesting to study all those advanced models, whether it's a large language model, computer model, or foundation models. Do you think there could be a mismatch between the data itself and the model? So how will you do study? How do you guarantee this to match, like in terms of the size, quality, diversity, and so on and so forth?
Yep. This is definitely the case. That's why internally right now we have specific track of, it's called like capacity versus data. So we need to understand this scaling laws. To what extent we can increase the capacity with more and more data. Because sometimes we don't have enough capacity, and just putting more data just doesn't help, just because we have low capacity model. Or for example, vice versa, we have a very, very good model that can be overfitted to literally every data that we have. We just increasing the capacity also doesn't help. So this is sort of, I don't know, the varied performance curve depending on the both capacity and data. And our approach currently is mostly we are trying to understand these two axes, how to work in the grid of like data versus capacity. And this is like internal approach, but whether, for example, the whole amount of data in the internet can be solved by current approaches, transformers, as I think mostly what we can see right now. This is open questions. Probably the overall solutions is to have the super simple model as possible with as small bias as it could be. And I think like even transformers have probably even more bias than MLP. Probably eventually we would solve everything by like 2-layer MLP. I'm not sure.
Okay. So now then let's have speaker.
Thank you.
Okay, so our next speaker is Shenglong Wang. So Shenglong is the assistant professor at University of Illinois, specializing in computer vision, robotics, and machine learning. And his recent research focuses on creating digital replica of the world and the simulation realistic new content to train and validate autonomous systems. Shenglong's past work received a 2020 IRAW Best Application Award finalist and 2021 CVPR Best Paper candidate. His research in self-driving technologies has led to the filing of over 25 patents. Wow, so Shenglong was selected as the recipient of Amazon Research Award and various fellowships from Facebook, Adobe, and Royal Bank of Canada. So he regularly served as area chair of Convision, Robotics, and AI conferences. So Shenglong, please.
Thank you. I use my own laptop. Oh, I connect.
So do you know how? No,
Yeah.
so do you know how to dial into the Zoom?
Yeah, I already in the Zoom. And
You
I will
just
share the screen.
you just share the screen. You can just share the screen. So we'll see that.
I see. May I actually use this one because I might have. I can actually connect and then share.
You can share on your Zoom.
I see. Okay. Like this, right?
Yeah, so it should be on.
Yes.
Okay, great. Thank you.
All right.
So
Great.
the camera is here. You can, if you maybe
Okay,
talk a little
I
bit,
see.
so-
I see. Okay. Yeah, sounds good. Yeah. All right. Thank you for the introduction and thanks for having me here. And today I'm going to talk about how can we build a platform to safely evaluate and validate self-driving autonomy. As we know, self-driving vehicles would potentially bring us a safer, more convenient, and low-cost transportations in future. That means that we haven't reached that stage for everybody to trust self-driving vehicles and have scale up our self-driving vehicle autonomy to the entire world. To me, my biggest concern about the challenge towards safe self-driving lies in the fact that we haven't reached a stage to be robust and to be very verifiably safe to handle all kinds of those long-tail safety critical scenarios. For instance, suppose we have kids that is standing in a sidewalk. Can we actually handle when the kid is suddenly crossing the street? Is there any guarantees for our autonomy stack? And for some very rare cases, say an elephant that is crossing the street, given the fact that our autonomy stack might not have seen so many elephants during the training stage, can we handle that? Or under some extreme weather situations, say during extreme, snowstorm, can we handle that? All of those are limited by the fact that is we don't have enough data for those kind of, safety critical and long tail situations. And I personally believe this is a key that we should solve, in order to build better autonomy. That being said, autonomy is restricted by the data. So today, my goal is, can we figure out a way that we can safely and reliably build an environment such that could potentially provide some data to train and evaluate how our self-driving vehicles can perform in those dangerous or extreme scenarios. So there are already quite a few paradigms that have been widely adopted in industry and in academia in order to train and verify self-driving safety. The most common cases is just leverage off-policy, offline collected data set. For instance, in academia, we often play with Kitty dataset, New Scenes dataset, Argoverse, and Waymo, etc. They collect realistic sensor data. That being said, there is a lack of a closed loop environment that allow us to train and verify the autonomy in the end-to-end fashion. So in the end, we could only test our performance on the perception side of things, or train off-policy, imitation learning and so on, which is quite restricted for us to build an end-to-end pipeline. So on the other side, we can go the other extreme. We actually build whatever, self-driving stack, and we deploy them on real world, right? That impose a safety concern. For instance, suppose we have some street workers that are trying to cross the street. Is that possible that we can evaluate that in the real world? In fact, it is either unethical or too costly to evaluate that. Another compromise is to build a test track. Say we have a test track, there's no real person. Instead, we use mannequins, basically the fake pedestrians and cyclists that I showed here. And we see whether our self-driving vehicle is able to react to those mannequins, right? Firstly, it's not scalable. And secondly, those mannequins will still bring cost to our vehicles in case a crash happens. So we want our self-driving vehicle to be safe, and also want no one or no pedestrians or no properties has been put in a risk while we want to train or test our vehicles. And another alternative that's been widely used in industry as well, that is called simulator, right? One of the famous one is called color simulator that have been open source for a few years, has advanced our field a lot. That being said, despite that, there are a lot of efforts have been put in building those simulation environment. There's still lack of realism. And also there is still a lack of the fact that the simulator only runs in computers. They are not bringing the real world and real hardware in the loop, right? So ideally, the ideal environment, it will look something like that. It's realistic in both sensor and physics. It's a closed loop environment that could potentially bring the real vehicle on board. And on the other side, unlike real world test cases, it's still safe. So we can test whatever safety critical cases without worry about ethical concerns or safety concerns. And that is our goal. And today I'm going to talk about, some steps my group and my collaborators have been working on towards pushing that step, towards this goal. So overall speaking, I'm going to talk about two parts. The first part is about the philosophy that in order to push a realism of simulation, we should definitely leverage real world data as much as possible. And the other, on the other side, for the properties that it might be really hard to simulate, we should directly bring the real world component into our testing pipeline. That means we should run a simulation in the real world, bring the physical world in the loop. So now let's firstly begin with what is needed for a driving environment. In order to build a simulator like Carla, we need at least three essential components. The first is digital assets. We need to create 3D meshes, animatable humans, and 3D environment in order to build the environment. On the other side, we need to simulate their behavior. Basically, we need to create a certain traffic scenarios, say a four-way stop sign, or certain traffic participant actors, such as a car that is violating the traffic rules, or a pedestrian, a jaywalker pedestrians, and so on. And third, after we create those words and create those assets, we need to be able to render them out and create realistic sensory observations. Say we want to create self-driving camera views, we want to create LiDAR perception sensors, and so on and so forth. So my group has been working on all of those 3 different components during the past few years, including creating digital twins for humans, cars, environment, or even animals. And also, we try to use generative models, create realistic scenarios and also behaviors. And due to the time constraint today, I will instead just focus on one aspect, that is how to simulate realistic sensory data under extreme cases or safety critical scenarios. So 2 years ago, my collaborators and I, we have been built a realistic, object insertion simulation pipeline. Essentially, given one video and given some of the digital twins that we have been built in the real world, we are able to insert those actors into our video, just like that actors are realistically interact within the surrounding environment and creating some of the safety critical scenarios. Note that this is not as trivial as we think. We might think we can just copy and paste the actors into the scene. That being said, there are some complicated interactions, such as the actor need to obey the traffic rules, need to be geometrically consistent, and also the lighting environment need to be consistent as well. So due to the time limit, I won't go into details, but essentially our insertion results looks pretty realistic. In this video, there are actually 2 actors that are not exist in the real world, that are inserted actors. Maybe you can, I will pause a little bit and then you can take a look and see whether you identify those fake actors. Any ideas? So those 2 are actually fake actors. They have been inserted, and as we can see, we have been relight the object such as it looks consistent in terms of lighting, and also they have been casted shadows that looks realistic. And this is another case where there are 2 actors that are running red light in front of a police car, which looks pretty cool, and that is something that is definitely very rare to see in the real world. And not only the Gaussian can be used for testing, but we could also use that as a form of realistic data augmentation. After we use those data augmentation to train our perception model, we can get a small boost in terms of IOUs for object segmentation and background segmentation as well. And it can be also generalized across different data sets. This is Argoverse, which has been taken in Miami, which looks pretty different from the previous data sets that we are using, but both are realistic. So now we are able to create some of the counterfactual scenarios and render them into a video footage in a realistic fashion, right? But we know that in extreme cases, there are not only just dangerous actors, but in some of the situations, we might face dangerous situations or holistic, domain shift in terms of weather conditions, right? This is a statistic that I find that might be interesting to you in terms of self-driving safety. So weather does impact driving safety. On average, there are more than 5 million vehicle crashes each year, and among them, more than 20% of those crashes are actually related with weather. So testing safety of self-driving vehicle under extreme weather is important. On the right, I show a very interesting research conducted by MIT that actually validate the accuracy of localization pipelines under extreme snowstorm, which is quite cool. But as we might notice that having those tests in the real world actually brings some additional risk, right? We know that even human drivers might not drive really well under those extreme weathers. Can we leverage realistic simulation to help bridge this gap and make sure our testing are safe? And the answer is yes. Let me show you a video. Here is just a regular playground, and we are able to build a neural scene of such a playground from just a single video footage. And now we are able to render from a different perspective. You're using a technique called neural radiance field. Next, I'm going to simulate different weather effects such as flood or snow or smoke, right, into this neural field by combining physical simulation and the neural radiance field so that it can produce a realistic video footage. And it's not only just a video footage, but actually it's a free view rendering of this entire scene. So we are able to render from all kinds of different perspectives so that we basically build a closed loop simulator of extreme weather situations. Here is some of the heavy smoke scenarios. As you can see, this looks pretty realistic. So the general pipeline will look like that. So given multiple input images that have been captured from different perspectives and also a target, weather impact. And we build a NERF model and using the neural radiance field techniques and with some of the improvement in order to increase the consistency between the different views and improve the quality of the geometry. And next, we use consistent style transfer, trying to transfer the visual style from a summer-like scene to a winter-like scene, right? You can see the vegetations become more green, become from greenish to grayish, and also the ground become more like whitish, right? Is this sufficient? The answer is clear, no, right? If we zoom in into a little bit, right, we can see the style transfer just essentially transfer some colors. It doesn't look realistic, right? There are something that is lacking, right? The stuff that is missing here is actually the physical entities of snow, right? We know in the snow scenes, we really want to see those particles of snows. That is something that in order to compensate, we'll have additional physical-based simulation stage. We literally drop, snow particles from the sky into the scene and stay on our ground and accumulate it so that we can simulate a realistic snow particles. This is similar applied to different scenarios like flood and smoke so that we can generalize across to any arbitrary videos that have been captured in the outdoor scenarios. And we know that this is a safe autonomous driving workshop. So we also apply that in self-driving vehicle data set, such as KT. And here we show different weather scenarios of KT, including smoke, and also what if the very nice little town Karlsruhe have been, flooded, or whether there is undergoing a snowstorm, right? We can simulate a realistic and consistent video footage of that. So of course, we want to test whether those self-driving perception system is able to perform well under those extreme cases. This is a state-of-the-art off-the-shelf, 3D object detector. And after we simulate the smoke, you can see the results have been slightly, tweaked and become more and more inaccurate. And eventually we might miss some of the objects under the heavy smoke. That suggests that this type of simulation is possible to help us to validate the perception performance under extreme weathers, and could potentially also bring some future research possibilities to leverage this to provide more training data for those extreme weather scenarios. Okay, so now we are able to create a realistic and data-driven simulation that trying to make our simulation to be more realistic in terms of sensor observations, right? We are able to build photorealistic, video footages of those different counterfactual scenarios, including the safety critical scenarios involved of pedestrians and cars, and also including extreme situations in terms of weather extremes, right? So that being said, this is still missing because we haven't bring the real world physics into the loop. Everything is still computer simulation based, right? We want to bring and build a closed loop simulation environment with the real hardware and physics in the loop. Towards this goal, we present a new work that is called CMON wheels. The general idea is simple. Suppose we have a real self-driving vehicle with a real autonomy that runs on board, and we have that self-driving vehicles to drive just on an empty parking lot. It's just an empty parking lot. And then we, instead of inserting the safety critical scenarios offline in computer-based simulators, we actually render them out online on the online perceived sensor streams. And then you can think about, we have mixed reality or augmented reality glasses installed for our vehicles. The vehicles, what the vehicle will see is something like in the background. It sees some virtual characters and it sees some virtual scenarios, and the vehicle need to react to those virtual scenarios in order to perform safely. So in this way, we can see we can clearly see the benefit, right? It's closed loop, right? Everything runs in the real world. Basically, we bring the real world dynamics and the real world, platform into the loop. There is no reality gap there at all, right? That being said, we are able to test the safety critical scenarios, because even if we crash in the safety critical scenarios, there is no consequences in the real world because the vehicle is just driving on the empty parking lot. And that is our base. That is a brief overview about the general ideas. So this is a pipeline that we show in the normal situations. Suppose we have the vehicles that is actively sensing from the physical world, and it will perceive some of the raw images. It's just an image of the parking lot, right? In the most common situation, we'll directly send our perceived images into the autonomy pipeline and see what autonomy will react to those scenarios. That being said, in our Sim wheels pipeline, we instead will insert some dangerous behavior, such as this lady is crossing the street all of a sudden, right? We'll render this scenario into our perceived images online, and then we'll send them immediately back to autonomy to see how the autonomy will react to those cases so that we can close the loop. And this is just the brief ideas and overviews about the Sim wheels. And also we have an onboard evaluation to immediately provide feedback, whether there's a crash, although it's virtual crash, right? Whether it's a crash or not happens in those type of situations, right? Here is the real video footages that we show there are some pedestrians that spawns and then trying to cut into the vehicle's path, right? In those situations, the vehicles slow down so that it yield to the pedestrian. There are no accident that happens. This is more extreme cases where the pedestrians are coming out of occluders. So the reaction time for autonomy here is as small as 400 milliseconds. In those situations, as you can see, the standard modular pipelines does not break on time, so that results in a crash in those situations. That suggests that our autonomy pipeline is not able to handle these safety critical cases. That being said, no one get hurt. So we are able to create multiple different safety scenarios like static obstacle, jailbreaker with occlusions, and traffic violations, and so on and so forth. And also our evaluation pipeline is agnostic to different autonomies, right? We can evaluate a perception, prediction, and action molecular pipeline. We can also evaluate an end-to-end imitation learner pipeline. In those situations, it's interesting that in the very easy jailbreaker situations, molecular pipeline is able to handle that well. That end-to-end imitation learning pipeline somehow it react too late, it break too late, so that it results a crash. That being said, on the contrary, on the extreme cases, because the fact that molecular pipeline take roughly 200 milliseconds to react, in those extreme cases, molecular pipeline is breaking too late. While on the other side, end-to-end pipeline because it's more reactive, so it actually is able to break. So it's worth note that in both of the scenarios, neither or one of those autonomy pipelines have seen that during training. Those are all novel, environment to those two pipelines. And here is another case of, traffic violations. We can see that the self-driving vehicle is able to react to it reliably for both. And next, of course, there is a question about how good your simulation is, right? So we need to validate whether the gap between our simulation and the real world is small. So we compare several reality gap comparisons. We start from image level, whether we create very similar sensors between the same and real. In order to do that, we actually put the actual chair on the ground, and we also put the chair at the same position in the simulation, and we compare one by one. As you can see from our naked eyes, it looks pretty realistic. And this is a traffic cone, and this is some other toolkits, and also two of my grad students. Basically, the general idea is we will build a digital twin of them, and we insert them into the world and compare, one by one. And we also compare their gap in action at the action level, meaning that, suppose we have the same scenario in the real world and in simulation. Does our entire autonomy pipeline react in a similar fashion, right? If we showcase that our simulator and the real behaves exactly the same, that basically help us to validate that our simulation is good enough to reflect the real world performance. Note that although the perception gap is not significant, there is still a noticeable, action gap. As you can see here, the final braking position are slightly different. There is roughly 20 to 30 centimeter off. This suggests that the perception or sensory gap between cinema and real might be propagated and magnified throughout the entire autonomy pipeline. This leaves some of the interesting questions for us to answer. So eventually, how can we minimize this gap for our downstream tasks? So we also quantitatively evaluate that in terms of both sensor and also perception intermediate results, where we compare the IOUs between the segmentation model, valid on sim and also valid on real, and also, evaluate the action gaps as well. And finally, we know that by bringing any new modules into the self-driving platform will bring additional latency, right? Compare against the standard autonomy, right? CMON will have the additional rendering stage, right? But we have showcased that on a low-end GPU like we use, which is RTS A4000, so the CMON will actually does not bring a very significant latency. It's roughly 70 milliseconds for an imitation learner, which is roughly, increased by 20%. That being said, it's still quite significant in terms of, relative performance. So still leave us a future study about how can we more efficiently render out our simulations in realistic manner. So to summarize, after we have conducted studies on realistic simulations using real-world data, and also bring the real world into the simulation, we are close to achieve our goal. That being said, given the fact that we want to run them on board in real time, our CMON will sacrifice a little bit in terms of realism. So we still have a long way to go in terms of pushing the efficiency and closing the sim to real gap, so that the simulation, especially hardware simulation, is able to perfectly reflect our performance in the real world. So my take-home message is simple. For dangerous scenarios, we should bring them into simulation to test because we don't want to bring any risk and harm. And also for simulation, for anything that we want to close the realism gap, we should try to leverage real data, real environment, real platform as much as possible. That is our insights that we have learned from those studies. And that leaves actually a very interesting future question that I would like to ask. This is a question that I got asked by my colleagues. I think this is particularly interesting to this workshop, where there are a lot of theoretical machine learning researchers who study guaranteed safeties and robustness in machine learning, right? Can I answer the question that would my simulator offer a safety certificate? In other words, suppose my self-driving autonomy has the scenario in simulation. Does that mean that I will have exactly same actions in the real world, or I would at least pass this safety check in the real world. At this moment, most of my results are empirical. I cannot give any theoretical guarantees yet, but I do think based on quantifiable gap between the simulation and realism, we might be able to answer this question so that simulation become a more, critical rules in the validation of safety rather than being just a supporting rule at this moment. And that summarizes my talk. I would like to thank my students, collaborators, and funding agency. I'm happy to take questions.
Any questions?
Hello.
Yes.
And thanks very much for your talk. And I want to know, we believe that the simulator is not just designed for the experts, but also for the anyone who want to use it. And we think the simulator needs to be more user-friendly. And I want to know the details for the ability to scale up for more data. And not only for a foundation model, but also for some manners for data augmentation.
Yeah, that's a great question. So I don't think any of the techniques that we have in the first component cannot generalize to any sort of data or end users. There does not need much expert. We just need someone who collects some videos, and then we are able to simulate. That is for sure. That is more like non-expert user friendly. On the other side, for the right side, it does require some expert knowledge and have access to a real-world vehicle platform. We do plan to open source the data so that anyone who has similar vehicle platform could use that. That being said, it's basically still restricted by the fact that we might need access to a vehicle platform. Yeah. Mm-hmm.
Okay, thank you.
Thank you.
And another question is that I think the simulator is designed by some kind of experts or knowledge, but I think some open vocabulary knowledge can be added to the simulator.
All right. Yeah. In regarding that part, for the interface of the simulator, there is still, I think there's still a lot of opportunity for us to leverage large foundation models, say language models, and trying to bring a very natural interfaces. Say anyone can read a sentence from the driving handbook. Say there's a four-way situations, create a four-way scenario for me. That will be really cool, and that is still a direction that is, I think, is definitely worth studying in future. Yeah.
Okay, thank you.
Thank you. And I do see there is a question in the chat. So the question is, in scenario generation, some works focus on related behaviors, others focus on related sensory data. Which one do you think is more difficult and which one is more important? This is a great question. So let me share my thought. My thought is in terms of scenarios, sometimes we need them to be realistic, but realistic is not necessarily the goal because we do want a domain shift. The domain shift is we want to shift towards more challenging and rare data itself, right? Because those data matters rather than only be more realistic. So it's not necessarily that scenario generation need to perfectly match. It just needs to be more reasonable. And regarding the sensory data, I do think there is a need to be as realistic as possible. Otherwise, we might not be able to bring the perception module into the loop to test end-to-end autonomy. Right? This is my thought. Any other questions? Yes, please.
Thanks. I think it's a very impressive and informative talk.
Thank you.
So I think the main idea of this is that we want to build a closed loop so that we can introduce simulation so that the evaluation and training is as close to the real world and like driving a car in the world as possible.
Yeah.
So my question is, say that ideally, you can run experiments, training and everything in the real world with a real car. Let's say that is 100%. And running simulation, like only generate simulation is like 0%. So it's kind of like special.
Yes.
And I believe that what you described is a pathway towards bridging the simulation to the real world.
Yes.
So my question is, how do you what's the roadmap in the future? Like how far are we in this spectrum towards a fully realistic simulation?
Okay.
So that like your final question would be if it passed a certificate in a simulation, and it could also pass this like it's equivalent to pass this safety certificate in the real world. Then my question would be like, what's the roadmap and how far it is?
Yeah, this is a good question. I don't think we can entirely solving the problem of simulation. Similar as I don't think we can entirely solve autonomy as well. Simulation is a really hard problem. I don't think it's it's easier than solving autonomy. So we cannot expect perfect simulator that exists. We can push the realism, close the gap, so that just like what you said. So in the future, we might have real world data collection still for most of the nominal processes to make sure that our autonomy still drive well in the real world. That being said, we'll put more efforts on real long tail, rare, unethical scenarios into the simulator, and then close the gap as much as possible with some certain theoretical guarantees. That will be the best roadmap to me. I don't think simulation can entirely replace the need for real world data collection. Most likely, we still need fleet of, say, Tesla vehicles or Wave or Waymo and Cruise vehicles that have been continuously collecting the data and verify their autonomy. That being said, we need to say something about some of the scenarios that it won't be able to allow us to test. That's my goal about how simulation eventually can help. That being said, simulation would potentially significantly reduce the amount of data that we need in the real world. My best bet will be we might need real world data collection, but we can create a significantly larger amount of simulation data and with a significant domain shift so that we have a more confident about our autonomy stack. Yeah, thank you.
Thanks. It's a great answer. Like my question is, could you please have some quantifiable, say that like how much % of real data can we save, and also like for example, how many fewer real world road tests can we any quantifiable things?
That is hard to give a quantifiable estimation because we can generate infinite amount of simulation data, right? Ideally, eventually it will be always 0% versus 100%. Suppose we generate infinite amount. I would say, I don't think the current amount of data is still enough for the real world data collection. We still need to scale up. The scaling law still applies. And I don't think any one of the company still have enough data at this moment. So we still need to scale up our real world data collection. Thank you.
I can comment a little bit. I think if only we save, I think we invested $300 billion in self-driving in the last 5 years. We can almost matter can save 1% of this 300.
It will be huge already.
That will be huge already.
Yeah.
So we don't need to be very confident about the 1%.
Yeah.
So we have last question.
Oh. The question is, how can we have assurance that we've bridged the real to synthetic gap for scenarios that are unlikely and hard to recreate in the real world, like car crash? And this is a really good question. So at this moment, I cannot have any assurance. I can have empirical evidence about how much the gap is, right? But the gap stays. And in order to have any assurance, we need more information about autonomy. Say, we might have a Lipschitz constraint about autonomy so that we can propagate our gap from simulation to the action. That means that significantly restrict the capacity of our autonomy pipelines. And we don't want that as well, right? So eventually it's a trade-off about how much that you sacrifice about performance to trade-off for theoretical guarantee. I hope there is no such a trade-off, but at this moment so far, there should be some of the sweet spot that we haven't looked into. This is a very good question for us to answer in future.
Okay, so let's ask our speaker.
Thank you.
So I think we'll have check the schedule. Yeah, we have a coffee break, and after that we'll come back at 3:20 for contributing talk. Thank you, everyone.
Yeah. And how do you think I'm also one of the startups that startup we like robotics from 120 meters, then try to get the buses, the cars, exactly. We sell this data to car companies. They can do it in the same way. Register so from that part, I'm not super expert in that part of the pipeline, but we first do reconstruction, and once we have that, we sign. So first there is this reconstruction phase, and then we register like every frame to the world, and then we have every real world position. Yeah, I'm more focused on detection and on tracking pipeline, so that's why I'm not an expert in this part of it. Yeah, so if you want to, you can also tell me something. They are not I think it's not on the website, but I could imagine that if you get in contact with
you mean the time space? I think he's going to but he's the best. He also does my something. Yeah, I'm working there as a PhD and also in some chair, and eventually the second PhD. Yeah, I think in recent times there's less work done on STEM, right? So, right. To address, for example, like in can I just schedule? Can you say again? National player release. So we can question for any other level this guy. Or not. Suppose you walk on office in some sample data. So that so at the moment, most of the data there is no drone and car vehicle simultaneously. There is when we're also starting to have like and potentially the drone. Yeah, but there will be also some requests for people asking for cars and drone. So if you're really interested in this, a lot of questions. Yeah, thank you. Thanks.
这肯定是，我觉得这个怎么说呢？我觉得这个 idea 大家都能想到，但是真的能做出来，就是说，比如说 simulator 对吧？这个对吧？可以熬回答的这个，但是其实我觉得做一下更好。好呀。我们不能说那我们现在也在做app 非常可以的，然后我觉得可以的，不过现在是和现在的这个概念不一样来定义一点，如果还让人现在然后这是不是说咱们不做，是就是这就做不了。对，我觉得所以说以后的话，就是这个现在这方就是说是 OK， 不能说我任何可能然后是吧？或者那你后边有那么长一个链儿，对吧？那么大 information， 一点点小 error 到后边肯定帮不住。所以我觉得想要做成这个虽改概念，让自己分然后但怎么改更有用？要一起去看。但是我觉得这个图说起来，有个图之后再快，然后我稍有一点哇，我想好明白。然后我就想就是说有一个可以就说那这个标准是我的主流改。但是它这里有一个悖论，给来嘛，就是说我最需要用 simulation 就是这些，这个东西的。我其实 real data 这个地方，我觉得不用一些，我直接就是好做了，但是就是common data 是最好的用 simulation 去替代，但是好像有并不太需要 simulation， 我们更需要 variance。
对，就是 rare cases 这个就是怎么说呢？这个就是比较难嘛。它因为这边跟这边这个这边就是啊，这个的对，没办法。对，所以说就像说那个说，我觉得这个问题就是，就是这个问题就是说，我们应该是说，不是我们是，它不应该是这个一来的，就是好和坏，和对和错，它应该是我们这个好多少，对吧？我就有5%的好，对啊，我就很好，就相当于我少出来5%data，或者我少出来6%。对，所以我觉得这个应该就是我们在一个里面打一个问题，就是说到底去定义simulation 的价值。对，我们现在已经在做了，已经用它了，它也有，然后其他就是就是一些那个其他的 application， 但是如果是一个公司就在这样在上打，我们但是我知道。就是你这样，就是说，如果说你知道它的一些东西，那你就可以做的是什么啊？就是以前我知道咋好，知道咋。如果你完全是立马不去学，对吧？那它这个就是说它有这个 spectrum， 就是说你如果说这个完全整个一般都完全知道的话，那么其实应该有个，其实就是得算出来，应该知道吧，对吧？它有些answer，你个answer你不知道你才知道吧。然后answer的话，如果它有这个你有你采样，对吧？你采样，特别是这个采样，你采一些的话，就是说这个，但是你不知道它的一些，那其实我经常也是他叫这个做 rate， 我觉得他做了很多非常清楚，是吧？不过因为他做太清楚了，所以说他的电影高不多，然后他现在在 Stanford 那个Stanford 跟政府的合作在不好，太好，就是这个，就他已经毕业了，然后对，你可以看到这个咱们这边是200多页把这个肉，我其实本来对，这个也这个就是像我们就是其实做了14个，做那个设计，然后还有那个对，这就是做了12年，然后我们其实刚刚去年还有一个大的这些都是就跟我们原先这个一站它原本来就不高的，然后每个你上每个 state 都高，那是太大了。根本就100或者高，然后怎么办？一些就是这个它的背景是网，它能跑这个所以它的对，这个数据很好。所以其实我们就是去年就是上午很多到Horizon 上架，然后对100多，现在确实对，你可以看一下然后去年的话就是然后大致到了100万，对，相当于对 input level 或者是你 force 的 input level， 然后就可以到提到，然后如果你电脑可以大，对，他把那个 first dimension 加了意思啊，然后 后应该是我觉得应该是挺好的。好呀，好，对对对，好，对呀，好，那就这样，拜拜。要不加个微信吧？哎，对，忘记。你是什么时候开始的？
我是开始1年半。确实，压力有点大啊，certainty 就是帮你们是吧？再慢慢开始来。
我现在基本就是做了都是基本就是1.2，当然有什么好就是他们带微信嘛，
然后学生都有很多比较成熟的学生可以帮忙，对，太想多了，
有个好多了，你差不多明白了。
继续努力。
我觉得就是非常幸运，就是第一个在就相当于他整个的先走了嘛。
对。好，谢谢，拜拜。
Hello, everyone. We have our contributed talk today. So do you have a laptop?
Yes, I do have it here, but I also have the PPT in here as well.
Can you download to Zoom?
Sure, I'll go on to Zoom.
Okay. And you can use this plugin, right?
Oh, yes.
So, okay.
I have.
I'll take my computer and if you can download to the Zoom.
Sure. Hello. It works, right? That said, do you mind taking a few photos of me presenting? I don't know what I need at the nation. Thank you. Screen share. Do this first, then. Can people on actually video as well? Can people on Zoom hear me and see me? I suppose. Oh yeah, thank you for confirming. So I'll begin. Thank you. I'll begin now. So thanks for having me. I'm Tong from Seoul National University. Today I'll be talking about my contributed work on overcoming temperature discrepancy and thermal image place recognition using edge-guided multimodal image-to-image translation. So basically, to begin with, when we talk about secure and safe autonomous driving, there are two disruptions to the systems that always naturally occurs. And majority of these affect either the computer vision algorithm or visual SLAM methods. And majority of these contributing disruptions either come from illumination variation or bad weather conditions, such as rain, snow, fog, etc. Well, in outdoor SLAM and odometry, we try to get around this problem using a different non-RGB sensor, such as thermal imaging. So thermal cameras operate in the long wavelength of the infrared spectrum. So it doesn't really capture reflected visible light, and it's large enough that it bypasses snow, fog, and rain particles. So there are two small, so as you can see on the image on the left, on the laser pointer, you can see that during night times or like a very sunny day with very light glare, we can't see anything in the RGB domain. Whereas in the thermal domain, you can see we can consistently maintain good visibility. But again, like thermal cameras have their own disadvantages. So this is supposed to be. So this, why isn't it playing? Okay, well, so the video on, so the video on the right is supposed to, so thermal images have this problem called automatic gain control that arises from when you are converting raw radiometric data into 8-bit visible data that ranges up to 256. And what usually happens is it is the method to so if you see on so before we talk about that, for those of you who do not know what visual localization or face recognition is, it's basically finding whether the picture, given Corey picture, is whether you are given two pictures, it's basically classifying whether you are in the same place or a different place. And it's being used a lot for SLAM loop detection tasks, as well as like visual localization in Google Maps and so on. So thermal images, as I said, they're good for being robust to illumination variations, especially during nighttime images. But as you can see on the images on the left, they are basically the images from the same place. But in thermal imaging, they look a bit different from one another. So the top image was captured from morning, the middle one from afternoon, and the last one from nighttime, they differ in appearance little by little. And this, again, is caused by something called, this happens because thermal images, you take temperature measurements and convert it into an image. But as we are taking temperature, it's usually colder in the morning and night times than in the afternoon. So in the afternoon, you can see that we get much more contrasts compared to when you take images from nighttime. So as a result of these shifting temperature distributions across different times of the day, we get appearance discrepancies between thermal images taken from the same place, but at a different time of the day. And when we directly apply this to existing visual localization algorithms for loop detection and stuff, such as DBOW, we get incorrect results, and it degrades the place recognition performance, which leads to degradation in autonomous driving performance. Well, was I the first person to be aware of this? The answer is no. There have been attempts in literature to tackle this problem. The first ever, well, I wouldn't say the first ever, but one of the pioneering works in this sector is the work done on the left, where they tried to use a linear interpolation mapping function as part of a bundle adjustment optimization to basically learn a fine transformation from to convert thermal image intensities of one thermal image to another thermal image. Essentially, basically, it maps one thermal image into closes the distribution gap down, basically. But the limitation of it is it's only been tested in few-hour time gaps. So if there are severe time, like longer time gaps, such as morning and night times, it doesn't really work that well. The other part is, of course, since we are CVPR, we like to harness the power of the deep metric learning, deep neural networks. So nowadays, people use visual localization using methods such as NetBLAT or any variants of it. But again, recent works, they've only tested these methods on indoor localization, indoor environments where the temperature distributions are not likely to be that severe compared to outdoors. But in our work, we actually tested it using given public data set and found that at outdoors, due to severe appearance discrepancies, they just don't work that well. So then how did we solve this problem? Our problem is our method is very simple to understand. In RGB images, you have things like turning nighttime images into daytime images to increase visibility on the image. Well, in thermal, we have a similar problem because of the whether the image was taken at cold night times or hot daytime. So during the day, we can say that the contrasts are high, because contrast of the images are high because daytime thermal image, because at daytimes it's pretty hot. But alternatively, at night times, the image contrasts are low because the histogram distribution or the variance of the histograms are very narrow, so that we don't get that much contrast. So our idea is, why don't we translate those images, whether it being daytime or nighttime, translate them into a unified single representation. So for example, as an analogy, I could say if I have a thermal image taken at 9 p.m. and have one taken at 2 p.m., why don't I use image translation network to translate them into as though if they were taken at 3 p.m. in the afternoon. And if that is to be the case, their contrast and their visual appearance somehow will be unified, and using that we could use it as a training data or just apply it to any conventional visual localization algorithm, and it should work out hopefully well. We'll find out. So that's our basic idea. So to briefly explain, if we have, like, as you can see, thermal images taken from morning, afternoon, evening, use our trained time-agnostic thermal image translation network, translated into like a unified representation. And if we use this to apply it to any video localization algorithm, such as DBOW or NetFlag, it should hopefully like give out correct results, and it did. So the objective of the image-to-image translation model, as I repeat, is to overcome the appearance discrepancies. Think of it as this way, like image histogram distributions from morning and night times, they differ greatly. If we use image-to-image translation to learn more of a nonlinear mapping to close down the distribution gap between images taken at different times, then we would be able to have unified views. So this is our proposed architecture. So now you might be saying, like, then why do you have like a separate proposed architecture? Why not use something like CycleGAN, which is very easy to train and off the shelf? I'll give you the reason for that later. But for now, so we have for image-to-image translations, we've set two domains. We call it nighttime and daytime, because at nighttime the contrast is bad, and daytime the contrast is relatively better than nighttime. So we have two domains, and then we basically have thermal images that are taken during night times and taken during daytime. Then we train the image-to-image translation model that essentially translates any thermal images into daytime representations. And we do this on top of, we use two models. So unlike CycleGAN, we build this on top of a multimodal image-to-image translation model called Munit. And we imposed two additional changes. The first change is we use Laplacive Gaussian loss, which is basically edge enforcing loss that can that penalizes the network for not preserving key objects in the translated image. And it's a good loss because we don't need any additional like edge maps, external edge maps to guide the training procedure. The second one is domain discriminator loss. So as you can see on the previous slides, since thermal images are grayscale, it's very difficult to distinguish between daytime and nighttime, even for humans. So we impose kind of extra penalty loss function, domain discriminator loss, to enforce the network to be able to classify, well, actually enforce like fine-grained details and how make it classify between whether the generated images from daytime or nighttime thermal images. So, well, this is our moment you've all been waiting for, the results. So we've used a public data set called Thero dataset, which recently came out last year, and it's nice because it has a lot of thermal images taken over 3 sequences, and the 3 sequences were taken at 3 different times of the day. I think it was 9 a.m. or 6 a.m., 2 p.m. and like 1 a.m. in the morning. And it has like multispectral sensor data, but we only took the RGB, the thermal, and the RTK GPS to use it as a place recognition or visual localization data set. And basically we formulated the face recognition data set based on this public data set, and we used the KAIST sequence as training, and we validated it using the Valley sequence. So there were no like, we used basically different sequences for training and testing to show that it generalizes not only to, well, it generalizes well to like unseen sequences. And for information, KAIST sequence is more like a city, urban kind of area. It's like a campus, basically, university campus. The Valley scene is more of a suburban, very foresty, riverside kind of environment. So their environmental types differ greatly. So these are the results. As I said, I didn't use CycleGAN from the beginning because, well, at the start I did use CycleGAN, but if we use CycleGAN, we can't really have control over which style. We don't have the control over the style of the images we translate into. We have what we want, translation consistency between images we translate. But since CycleGAN uses like a deterministic mapping learns function, we can't really have controls over it. And moreover, CycleGAN is very well known for being under constraint. So it doesn't really preserve like key semantic details like cars and buildings in the translated image. And today GAN is a variant of CycleGAN, specialized for translating nighttime RGB into daytime RGB images. We have basically taken the same architecture and retrained it using the same datasets. And min-max is the original thermal images. And as you can see on the red and yellow boxes, we are able to preserve key semantic details presented in the original min-max thermal images. In addition, as you can see, our image contrasts are much more uniform than any of the other methods being used. So this is only the qualitative side. If you look at the quantitative side, we've evaluated our method using both traditional and learning-based visual localization methods. So NetFLAD is a learning-based, like the de facto go-to learning-based visual localization method. And on NetFLAD, we outperformed the traditional way of visual localizing on thermal images, as well as we've applied the translation using different translation networks and see if it worked. And aside from our network, if you use any other translation network that we chose as baselines, they degrade the place recognition performance. But when you use our method, it ameliorates the place recognition performance. And the same trend continues for the DBOW, which is the conventional handcrafted feature-based place recognition method. And from the PR curve, we can also see that we have the most area under the curve, showing it achieved the highest visual localization accuracy. So we have to talk about the selection of styles. So styles basically refer to like a reference thermal image to translate into. So if you have, you could have like multiple different styles to all thermal images to translate your original images into. And depending on the style, their appearance changes little by little. But we found out that style selection is a very important procedure in executing PR, because depending on which style you use, the place recognition accuracy greatly differs a lot. And you may have a question like saying, how do you select the optimal style, weighted style vector for thermal images? There are no set way, like distinct ways, but a tip of a hint is if you look at the edges preserved between the original and the translated image, those with highest SSIM comparisons between the original and the translated image tends to have the highest, tends to be the optimal latent styles. So the conclusion is thermal images, thermal images, they have these appearance discrepancies that arise from the natural temperature drifts that arises from temporal time differences. And they make place recognition not work that well in real autonomous driving scenes. But if you use our generative network, you can reduce the appearance discrepancies and improve the place visual localization performance. And yeah, there should be further considerations for selecting optimal adaptive styles. And yeah, that's it for the presentation. I'd be happy to take any questions. Thank you.
Thank you. Are there any questions? If there are any questions, you can just ask.
Well, there doesn't seem to be any questions from the audience just yet. They all seem to be enjoying their nice little coffee breaks.
Okay, if there are any questions, maybe we can continue to our next talk.
Okay. Well, thank you.
Thank you for your talk. And due to the visa issues, we need to do the online presentation for the following contributed talks. So can everyone in the room please log into our Zoom in order to join the next two presentations? We will start the following talks in 5 minutes. And sorry for the inconvenience caused. We have made effort to ensure a seamless experience, but we still need to do the online for the two talks. Thank you for your understanding.
Good afternoon, everyone. Can everyone see my screen now?
Maybe we can wait for another 2 minutes for the in-person ones to join our Zoom.
All right, thanks. Then 2 minutes later. Yeah.
I think maybe most of us joined our meeting. So the next talk is from Chibi. He will be presenting his talk titled Instance Normalization Transformer for Generalized Driving Scene Segmentation. Let's welcome Chibi for his presentation.
All right. Good afternoon, everyone. My name is Chi from the Computer Vision Research Group, University of Amsterdam, the Netherlands. It is really a pity that today I can only give this presentation online because of the visa issue. Also, on behalf of my co-authors, Dr. Shaodi Yu and Professor Theo Gavers, I'm here to deliver one of the latest works in our research group entitled An Instance Normalization Transformer for Generalized Driving Scene Segmentation. First, about the problem definition. Generalized driving scene semantic segmentation refers to the scenario when a semantic segmentation model is trained on a certain driving scene is supposed to show good inference on unseen driving scenes. It is very important because many real-world applications and trustworthy AI systems, such as autonomous driving, demand great generalization ability for a model. However, this problem is particularly challenging mainly because of the great style variation. The style variation can be caused by the weather conditions, lighting conditions, and urban landscape variation. What's new in our work? In this work, to the best of our knowledge, it is the first approach to use vision transformer for generalized driving scene semantic segmentation. To this end, we propose an instance normalization transformer, in short, INformer, for this task. Also, empirically, a more than 12% MIOU improvement can be observed compared with the state-of-the-art methods. About related work, 5 commonly used driving scene segmentation datasets have huge domain gap due to the great style variation. The first dataset is the cityscape dataset. It has been widely used for the computer vision segmentation community. The samples are mainly from the German streets and are taken under a favorable weather condition, such as cloudy or sunny. The second driving scene segmentation dataset is the BDD100K dataset. The samples are taken from the United States landscape, and the samples are from a more varied lighting conditions from different times of the day. The third dataset is the mapillary semantic segmentation dataset. The samples are taken from globally, all over the world. Also, the samples are of more varied both weather and lighting conditions. The fourth dataset for driving scene segmentation is the GTA5 dataset. The samples are from a simulated United States street landscape. Although it is simulated, the samples are from varied lighting conditions. The fifth dataset is also a simulated dataset. Its name is Cynthia Semantic Segmentation Dataset. It is also from a simulated urban scene, and the samples are from a lot of varied lighting conditions. Then, about the concept of domain generalization. Domain generalization assumes that the target domain is inaccessible during training. It aims to improve the generalization ability on unseen target domains. The below figure gives a brief concept illustration of domain generalization. Indeed, there are extensive works in both computer vision and machine learning communities under the low task specific settings. However, these low task specific methods are usually not effective enough to handle the great style variations in driving scenarios. Also, about domain generalized semantic segmentation. Earlier works usually directly use instance normalization or whitening transformation on CNN-based segmentation models. Recent state-of-the-art works can be categorized into 2 types. The first type is to use more robust style decorrelation approaches. Some typical works include instance selective whitening and semantic aware whitening. The second type is to introduce more advanced adversarial domain training techniques to enrich the style diversity. Some typical works include the adversarial style augmentation and whitelet. However, to the best of our knowledge, these methods are CNN-based. The CNN features compared with the more powerful features from Vision Transformer limit the content representation ability. Then, this figure gives an overview of the proposed framework. The goal is very simple and straightforward. It is to make the feature embedding from the Vision Transformer to be robust to the style variation. To realize this goal, we implement the instance normalization in both encoding and decoding stage. Besides, the feature fusion in the decoding stage is in a progressive manner. Another preliminary is about the instance normalization transformation. To be short, instance normalization implements the channel-wise normalization from the deep features. In the encoding stage, the features from the image encoder, let's say a swing transformer backbone, are implemented with the instance normalization. Then, in the decoding stage, the features from each scale of the image encoder are implemented with the instance normalization transformation. After that, the normalized features are fed into the transformer decoder in a progressive way to generate the semantic predictions. The transformer decoder is directly inherited from the original mask-to-former, which is a state-of-the-art mask-wise segmentation model. For other implementation details, the loss functions and hyperparameters also keep the same as the original mask-to-former. Then, about experimental validation. The first experiment is the state-of-the-art comparison. Our proposed ion former is compared with some state-of-the-art methods, including IBNet, instance whitening, instance selective whitening, shade, semantic aware whitening, and widenet. The first setting is to train the model on cityscape dataset as the source domain, and then validate it on the rest 4 datasets as the target domains, respectively. So first, let's see the results on the BDD target domain. A more than 8% MIOU can be observed when compared with the strongest state-of-the-art. In the right side of the slide, some visualized predictions from our ion former and the instance selective whitening are compared. The proposed ion former is more capable to separate the road from building, which is crucial for autonomous driving. Also, when you use the mapillary dataset as the target domain, a more than 10% MIOU can be observed compared with these CNN-based state-of-the-art methods. And also, on the mapillary dataset, the proposed ion former on the right side of this slide is more capable to separate the road from the vehicles and the buildings. Similarly, when you use the GTA dataset as the target domain, also a more than 10% performance MIOU can be observed and more reasonable predictions can be yielded. And when use another simulated dataset, Cinza, as the target domain, also a more than 10% MIOU can be observed compared with the strongest state-of-the-art. The second experiment setting is more tricky and more challenging. It uses the GTA dataset, which is a simulated dataset, as the source domain, and then validate the trained model on the rest 4 datasets as the target domains, respectively. First, when you use the cityscape as the target domain, a nearly 10% MIOU can be observed when compared with the state-of-the-art methods. And the right side is some visualized predictions. And similarly, when you use the BDD dataset as a target domain, a more than 10% MIOU can be observed compared with the CNN-based methods. And still, the proposed I-informer is more capable to separate the cars from the road and building, and it yields a more reasonable semantic prediction. And on the map theory dataset, also a more than 10% performance gain can be observed when compared with the strongest state-of-the-art. And notably, compared with the commonly used instance selective whitening methods, a nearly 20% MIOU performance gain can be observed, and it shows a more reasonable inference to distinguish the road from trees and buildings on this setting. And similarly, on the SynSat target domain, similar results and observations can be found. The second experiment is the ablation studies. Please remember that we implement the instance normalization on both encoding and decoding stage, which we call encoding normalization and decoding normalization respectively. The encoding normalization can lead to an up to 1.97% MIOU gain on these target domains. And for the decoding normalization, the performance gain can be up to more than 4% MIOU on these target domains. The normalization in the decoding stage is more significant than the encoding stage because the features from each scale are implemented with the instance normalization in the decoding stage, which helps the features to be more robust to the style variation. Finally, the conclusion and summary. In this work, we investigate the possibility to adapt the vision transformer for the generalized driving scene semantic segmentation. To this end, an instance normalization transformer, in short, I-informer, is proposed. Its key idea is very simple and straightforward. The feature embeddings in vision transformer are normalized during both the encoding and decoding stage in a progressive manner. Also, extensive experiments on multiple domain generalization settings show the state-of-the-art performance of the I-informer against existing CNN-based methods. Also, a more reasonable semantic prediction is observed by the proposed I-informer. This is all of my presentation. Thanks for your attention. Thanks.
Okay, any questions? Okay, yes, thanks for this presentation. Let's welcome our next speaker, who will present the paper 3D CMA, 3D convolution with mask attention for your vehicle speed estimation.
Hello, everyone. Good evening.
Hi.
Okay, let me share my screen. Just give me a moment. Yeah, is my slides visible?
Yeah, let's start.
Sure. Okay, so a very good evening to all of you. I would like to get started by thanking the organizers for making this event hybrid in order to accommodate folks like ourselves who couldn't, make it to the event in person. We are from the research department at this company called Elm Company. We are headquartered in Riyadh in Saudi Arabia. Probably I will spend a minute to explain some of our activities and research towards the end of my presentation. So I wouldn't spend more time on it now. So without further ado, let me get started. So our paper is titled 3D CMA, 3D convolution with masked attention for ego vehicle speed estimation. So what we aim to do is that given a sequence of images from a monocular camera, we developed a deep neural network that can regress the speed of the vehicle in which the camera is mounted. I think this is best represented using this image, if you can see my mouse that have pasted here on the right, where we take in images at fixed time intervals, let's say Tn-1 all the way to Tn+3. And we feed this image sequence into the model, which in turn regresses the speed of the vehicle in meter per second or kilometer per hour, and so on. So the question is, what is the motivation behind having a solution like this at hand? So the motivation is to have a standalone solution that does not depend on, in-car sensors to extract the vehicular speed, such as maybe from a canvas for various ADAS use case where modularity is a constraint. We also want it to be commercially viable because we have seen prior works that may use the IMU sensor and maybe some even to an extent of using multiple sensors like, the monocular camera along with the LiDAR and so on. So the cost effectiveness of the solution was also the motivation behind going for a simple monocular camera based speed regression technique. And yet another use case where we think this is really good is, the capability to have an ego vehicle based speed estimation. It serves as the main ingredient for having a mobile speed estimation solution. So this means moving speed cams. So we are typically used to, seeing speed cams mounted at fixed locations, but you can imagine having such a kind of solution, if we work in collaboration with the government entities wherein we can have these solutions deployed inside patrol vehicles, and these vehicles move inside the city and, maybe to find the speed of environment vehicles, violators, overspeeders, and so on. So yes, so when we get started to work on this, we wanted to measure the effectiveness of our AI algorithm, or in other words, we wanted to benchmark our data. So for the benchmarking purposes, we have relied on two public data sets. One is the very famous Kitty dataset. I've just placed some example video samples from the Kitty dataset. And we also use the new images dataset for our evaluation. So the Kitty dataset is sampled at 10 Hertz, while the new images dataset is sampled at around 2 Hertz. I'm not sure if it's fully visible here, but I have put in a split of the train and the test samples. And one main gap that we identified in the data that's available in the public data sets is the spread of the speed values that's available. All of these public data sets have speeds in meter per seconds up to maybe say 15 meters for the new images, and let's say up to 18 meters per seconds for the Kitty data set. And we think that this makes sense because all these data sets such as the Kitty and the new images, the data collection of vehicles are mounted with a multitude of sensors, and they have the ground truth annotations for a lot of applications ranging from end-to-end autonomous driving and so on. So, such a heavy sensor suite of multitude of sensors often limits the capability of the car to move at really high speeds. But this is something that is lacking because when you have a very mobile solution that can be mounted as a dash cam, then we would expect data to be available, for speed ranges from, let's say, from 100 kilometers per hour or 120 kilometers per hour, or maybe even 140, depending on the expressway and the highway that you're using. So in order to bridge this gap, we also worked on some real data set. And in addition to that, we worked on some synthetic data set, which we call it as the SEVS data set here. So this data set bridges this gap and provides a continuous stream of speed ranges from 0 to 140 kilometers per hour. So I've put in some data samples here from our synthetic data. The first video here, you can see that there is no ambient lighting. The vision or the light is coming just from the ego vehicle. The second video stream, you can see that there is sandstorm coming in. So we account for such variations in terms of the environment, such as, whether it's sandstorm or if the sun is shining directly at you and so on. And it's another variation of the night itself, but you can imagine the light coming in from the moon. So there is some ambient lighting in the environment. So the visibility is slightly better. And in this case, we also accounted for variations in terms of the texture of the road and also the kind of lane markers that are used, whether the lane markers are going to be solid lane markers or cat-eye lane markers, for instance. Yet this example shows the sun directly shining at the ego vehicle. So the projections, the shadows, and everything follows the physics behind it. So in order to make this possible, we used the Blender rendering tool, the 3D modeling tool, and we used the Rig a Car add-on in order to control the vehicular speed. So we were able to simulate the ego vehicles driving, from stationary to all the way up to 140 kilometers per hour. And we collected about 250 samples, and each sample comprising of about 10 to 15 seconds. And we accounted for variations in the focal length of the camera in order to add more variations into the data set. But we also altered the height of the placement of the camera and so on. So yeah, this is some sneak peek into the SEVS data set that we developed for this particular application. Now, before we get into the evaluation, I would like to talk a bit about the network architecture here. So we taken, as I mentioned, it's a continuous stream of video. So we taken image streams and we use a pre-trained model to extract the masked input here. And later the masked input is concatenated along with the RGB or the monocular camera stream, and we call this as the masked attention input. So the masked attention input is further fed into the neural network, which follows a series of convolution and max pooling layers before we finally flatten it and regress the speed value. So in terms of the loss function, we have used the RMSE loss, where SI over here correspond to the ground truth speed, and SI hat correspond to the inferred speed. So the inferred speed SI hat can be further decomposed into W transpose X, where W stands for the weight vectors for the 3D convolution filters, and X can be further decomposed into the image component and the masked component, which together, when concatenated, form the masked attention input. One of the design considerations that we had while designing the neural network was to, say, for instance, use a convolutional 3D convolutional filter of, say, 1x2x2 in the initial max pooling in order to preserve the temporal information and make sure that the temporal information doesn't get lost as we proceed further into the network. Now moving on, I would like to talk about some evaluation that we did on the public data set, namely the new images, the Kitty and the SEVS data set. In order to compare the performance of our algorithm, we've used the VIVIT, which is the vision transformer. And we think the vision transformer is good for this particular comparison. It's fair for this comparison because this is the variant of transformer that's tuned for video vision, and vision transformer has the capability to be a fair comparison to the 3D convolution because of the presence of the tubelet embeddings. So we did some evaluations, and these are the numbers, the evaluation metrics in terms of the RMSE and MAE. On the new images, we observed about a 27% improvement using our 3D CMA approach in RMSE and MAE. And for the kitty, we observed roughly about 30% improvement. And finally, for our synthetic data, the SEVS data set, compared to the VIVIT, we noticed an improvement of about 40% in the RMSE and the MAE. Now, the next question was to understand in the form of some kind of an ablation study, where we wanted to know what was the real contribution that the masked attention brought onto the network. So we discarded the VIVIT and used a traditional or a regular 3D CNN without the masked attention and compared it with our 3D CME, the 3D convolutional network with masked attention. And we noticed similarly on the new images about 30 to 35% improvement in the RMSE and MAE, while for the kitty data set, there was an improvement of about 25% for both the RMSE and the MAE. In addition to this, we also did some cross data set evaluation. And of course, when we train on one data set and the test on the other one, you can see that there is a noticeable increase in the RMSE and the MAE. But even under this format of consideration, the 3D CMA was giving much better scores for the RMSE and the MAE when compared to the VIVIT. So now we spoke about the evaluation for the public data set. As I said, we are a research company, and we focus a little more about how this translates into real world situations. So I thought it's good to include some examples wherein we actually tested our algorithm on some real world data. And you can see here in yellow, I've highlighted the ground truth value, and the prediction from our AI model is outlined up on top. I hope the numbers are visible here. And the one on the left is more about a fast moving car scenario. And I incorporated also a slow moving scenario where there is more dense traffic and so on. So most of the times we see that it's in agreement, wherein we see an error of about within 5 km/h variation between the ground truth and the prediction. So yeah, I think that's about my presentation today. I hope the above slides give some intuition into our work for ego vehicle speed estimation. So as I mentioned at the start, I will spend just a minute to talk about our research areas and ELM research. So we at ELM research, we focus on we have different verticals of focus, starting from computer vision to NLP, to data science, to blockchain, to IoT, sensors, robotics, drones, and AVs as well. Recently, we set up an offshore center in London for the autonomous vehicles and related use cases. So if you're interested to learn more about our research activities, you're free to scan our QR code here and learn more about the company. So that's about it. I would like to thank the attendees for your time and patience. And once again, thank the organizers for the workshop and this opportunity. So thank you again. Enjoy your evening and have a good day. Thank you.
Okay, thanks for the presentation. Any questions? Okay. Yeah, I personally really like this cool idea. Like you don't need any additional hardware to estimate the speed. Yeah, that's cool. Okay, we'll move to the next session, which is a poster session and a break. So I think we have in-person poster in the conference room, and we also have one online poster. The presenter will share the screen of the poster, and the other posters can be seen in the conference room.
Hi, everyone. As we near the end, I would like to thank you all for your outstanding contributions throughout this workshop. It has been a truly remarkable experience, and we are grateful for your participation. If there are any questions or thoughts you'd like to share, please don't hesitate to reach out to us via email, and we are happy to assist you further. Once again, thank you all for being part of this incredible journey, and we are going to close this Zoom room in 1 minute. Thanks.
Thank you, Shijin.
Thank you.
Thank you.